Hello there and welcome back to the Science Sleepy Minds, that cosy little corner of the internet where we transform the most mind-bending discoveries of our universe into the softest pillow your brain has ever rested upon. Tonight, you find yourself standing at the edge of something enormous, literally. Picture yourself descending into the earth, 100 meters down, past layers of ancient rock and sediment, past the fossils of creatures that swam in prehistoric seas, until you reach a tunnel so vast it could swallow entire cities. This is the Large Hadron Collider, and somewhere in its 17 miles of supercooled magnets and particle beams, scientists have just found something that wasn't supposed to exist. A crack. A fissure in the very foundation of everything physicists thought they understood about reality. You probably won't survive this journey with your comfortable assumptions about the universe intact, but then again, that's precisely why you're here. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, drop a comment letting me know where you're listening from and what time it is in your little corner of the world. I always love knowing that someone in Tokyo is drifting off just as someone in Toronto is starting their midnight contemplation. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You step out of the elevator and the air hits you first. Cold, impossibly clean, carrying that peculiar metallic taste that comes from being surrounded by more computing power and electromagnetic precision than anywhere else on Earth. The tunnel stretches before you in a gentle curve, its concrete walls lined with cables thicker than your arm, each one carrying signals that travel at nearly the speed of light. This is CERN, the European Organisation for Nuclear Research, straddling the border between Switzerland and France like a scientific colossus with one foot in each country. The year is 2024, though down here time moves differently. Scientists work in shifts that blur day into night, their eyes fixed on screens displaying data streams that look like abstract art, but contain the deepest secrets of existence. The Large Hadron Collider itself is a ring, a perfect circle buried beneath farmland and quiet villages, where cows graze obliviously above the most powerful particle accelerator ever constructed by human hands. When it operates, protons, those tiny positive particles at the heart of every atom, race around this ring at 99.9999% the speed of light. They complete 11,000 laps every single second, guided by superconducting magnets cooled to temperatures colder than outer space. And when two beams of these protons collide head-on, they create conditions that haven't existed naturally since the first fraction of a second after the Big Bang. You're essentially standing inside a time machine, one that recreates the birth of the universe billions of times per day. Now, here's where things get interesting, and by interesting, I mean the kind of interesting that keeps theoretical physicists awake at 3 a.m, staring at their ceiling and questioning their entire careers. The experiments at CERN are designed to confirm what we already know, or at least what we thought we knew. The standard model of particle physics has been the reigning champion of scientific theories for over 50 years. It describes everything from the quarks inside your atoms to the forces that hold molecules together. It predicted the existence of the Higgs boson 2 decades before anyone found it. The standard model is, by any reasonable measure, the most successful and precise theory in the history of science. And yet, the data coming out of CERN lately has been wrong. Not dramatically wrong, not explosively wrong, but wrong in the most unsettling way possible. Subtly, persistently, impossibly wrong. Historians of science still argue whether the greatest discoveries come from moments of brilliant insight or from the slow accumulation of tiny anomalies that refuse to go away. The story of CERN's crack in reality falls firmly into the second category. It started with whispers, really. A measurement here that didn't quite match predictions, an experiment there that showed results just slightly outside the expected range. Taken individually, each anomaly could be dismissed as statistical noise, the natural fuzziness that comes from measuring things at scales so small they make atoms look like beach balls. But taken together, a pattern began to emerge. Something was tugging at the edges of our understanding, and that something refused to be ignored. The control rooms at CERN look nothing like the dramatic command centres you see in movies. There are no flashing red lights or urgent alarms. Instead, you find rows of ordinary desks, cluttered with coffee cups and family photos, where physicists in casual clothes stare at monitors displaying numbers that would mean nothing to most humans, but represent entire lifetimes of work to those who understand them. It was in rooms like these that the first hints of trouble appeared. The muon, a particle similar to an electron but heavier and more unstable, was wobbling. Not in any way you could see with your eyes, of course. We're talking about quantum mechanical wobbling, the way a particle's magnetic properties shift as it interacts with the vacuum of space itself. The standard model predicts exactly how much a muon should wobble. The measurements at CERN said otherwise. Here's a quirky little detail that might make you smile. The original calculations for muon wobbling were done partially by hand, by physicists using pencil and paper in an era before computers could handle such complexity. They filled notebooks with equations, checked each other's work over long lunches, and eventually arrived at a prediction so precise it specified the muon's magnetic moment to 10 decimal places. That level of precision is like measuring the distance from Earth to the Sun and being accurate to within a human hair. And now, decades later, with computers millions of times more powerful than anything those original physicists could have imagined, the experiments are saying those calculations were slightly off. Not by much. But in particle physics, slightly off is the same as completely wrong. You lean against the cool wall of the tunnel and try to grasp what this means. The crack isn't visible, of course. You can't see it in the polished steel of the beam pipes or the blinking lights of the detector arrays. But it's there, hiding in the data, a gap between what should be and what is. Some scientists call it the most exciting development in physics in a generation. Others call it a statistical fluke that will evaporate with more data. But everyone agrees on one thing. If the crack is real, if something genuinely lies beyond the standard model, then everything we thought we understood about the universe, about matter, about energy, about the very nature of reality, will need to be reconsidered. The hum of the machinery surrounds you like a mechanical lullaby, and you realize that you're standing in one of the few places on Earth where the boundaries of human knowledge are actively being pushed outward. Above you, the world continues its ordinary routines. People are eating dinner, watching television, arguing about politics. But down here, in this cathedral of science, the priests of physics are confronting a heresy that might just turn out to be a revelation. The standard model sits at the heart of modern physics like a magnificent clockwork mechanism, every gear interlocking with perfect precision, every spring calibrated to tolerances that border on the miraculous. You've heard of it before, probably, even if only in passing. That vague sense that scientists have figured out the basic building blocks of everything. But standing here in the quiet hum of CERN's underground cathedral, you begin to appreciate just how extraordinary this theoretical framework really is, and why its potential cracking feels less like academic drama and more like discovering a fault line beneath your house. Picture the universe as a Lego set, except the pieces are infinitely smaller than anything you could hold between your fingers. The standard model tells us exactly what those pieces are. 6 quarks with whimsical names like up, down, charm, strange, top and bottom. 6 leptons including the familiar electron and its heavier cousins the muon and tau. and a collection of force-carrying particles that mediate the fundamental interactions holding everything together. The photon carries electromagnetism, allowing light to travel and magnets to stick to refrigerators. The gluon holds quarks together inside protons and neutrons through the strong nuclear force. The W and Z bosons manage the weak nuclear force, responsible for certain types of radioactive decay. And presiding over all of them, giving mass to the particles that have it, sits the Higgs boson, discovered right here at CERN in 2012, completing the Standard Model's magnificent architecture. For 50 years, this framework has predicted experimental results with stunning accuracy. When physicists calculated the magnetic moment of the electron using Standard Model equations, they arrived at a number that matched experimental measurements to more than 10 significant figures. That's like predicting the distance between New York and Los Angeles and being accurate to within the width of a single atom. No other theory in the history of science has achieved this level of precision. The Standard Model doesn't just work, it works so well that it almost feels like cheating, like someone handed humanity the answer key to a cosmic exam. And yet, even from the beginning, physicists knew something was missing. The Standard Model is brilliant, yes, but it's also deeply incomplete in ways that become more troubling the longer you stare at them. For one thing, it says absolutely nothing about gravity. That force pulling you toward the center of the Earth right now, the same force that keeps planets in orbit and galaxies spinning, the Standard Model treats it as if it doesn't exist. General relativity handles gravity beautifully on large scales, but when you try to combine it with quantum mechanics, the mathematics explodes into infinities and nonsense. This isn't a minor footnote, it's a gaping hole at the foundation of physics. Then there's the matter of dark matter and dark energy, which together make up roughly 95% of the universe. The Standard Model accounts for the remaining 5%, the ordinary matter that forms stars, planets, and everything you've ever touched or seen. But that invisible majority haunting the cosmos, not a word. The Standard Model simply shrugs and looks the other way, as if pretending dark matter doesn't exist might make it go away. Historians still argue whether the Standard Model's architects were aware of how incomplete their masterpiece would turn out to be, or whether they genuinely believed they were closing in on a final theory of everything. Here's a quirky detail that might amuse you. The Standard Model contains about 19 free parameters, numbers that can't be derived from any deeper principle, and simply have to be measured experimentally. These include things like the masses of various particles and the strengths of different forces. Why does the electron have exactly the mass it has? Why is the strong force precisely as strong as it is? The Standard Model offers no explanations. It just accepts these numbers as given, like a recipe that tells you to add exactly 3.7 grams of salt without explaining why that amount produces the perfect flavour. Some physicists find this deeply unsatisfying, a sign that something more fundamental must lie beneath. The theory also has what's called the hierarchy problem, and this one is genuinely strange. The Higgs boson, that particle responsible for giving mass to other particles, has a mass of about 125 billion electron volts. That sounds like a big number, but in particle physics terms it's puzzlingly small. Based on the quantum fluctuations that should affect the Higgs field, its mass ought to be enormously larger, something like 100 million billion times bigger. The fact that it's not requires either incredible fine-tuning of the underlying parameters or some new physics that naturally keeps the Higgs mass in check. Imagine balancing a pencil on its tip and having it stay there for 13.8 billion years. That's roughly how unlikely the Higgs mass seems without some additional explanation. You wander through the detector hall now, past towering structures wrapped in cables and sensors, each one designed to capture the debris of particle collisions and reconstruct what happened in those fleeting instants of cosmic violence. The scientists who built these instruments believed in the Standard Model. They designed their experiments assuming its predictions would hold true. The detectors are calibrated to see exactly what the theory says they should see. And for years, that's precisely what happened. Collision after collision confirmed the Standard Model's accuracy. The Higgs boson appeared exactly where it was supposed to. The decay rates matched the calculations. Everything worked. But physics has a way of humbling its practitioners. The same precision that made the Standard Model's successes so impressive also made its failures impossible to hide. When the muon experiment started showing that persistent wobble beyond predicted values, there was nowhere for the discrepancy to hide. When the beauty quark decays came up with unexpected ratios, the mathematics offered no escape routes. The Standard Model, for all its genius, had begun to show its age. What makes this moment so fascinating is that physicists aren't seeing the Standard Model collapse in some dramatic fashion. There's no explosion of contradictions, no experiments returning results that flatly contradict predictions. Instead, there is something more subtle and perhaps more profound, a pattern of small deviations, each one hovering at the edge of statistical significance, each one pointing in roughly the same direction. Taken individually, any one of these anomalies could be dismissed. Taken together, they suggest that the Standard Model is not the final word on reality, but merely an approximation, extraordinarily good within its domain, but missing something fundamental. The question that echoes through the corridors of CERN, whispered in coffee breaks and debated in conference rooms, is devastatingly simple. What lies beyond? The Standard Model has been a prison of sorts, its very success constraining physicists to work within its framework. Now, for the first time in decades, the walls of that prison are showing cracks, and behind those cracks, something vast and unknown is waiting to be discovered. You press your hand against the cool metal of a support beam and feel the faint vibration of machinery operating in the distance. Somewhere in this labyrinth, particles are colliding at energies that replicate the dawn of time, and in the data streaming from those collisions, the future of physics is slowly taking shape. The muon never asked to be famous. It arrived in the particle physics scene back in 1936, discovered in cosmic ray experiments by Carl Anderson and Seth Neddermeyer, and immediately caused confusion. The physicist Isidore Rabi famously quipped, "Who ordered that?" when confronted with this unexpected particle, a question that captures the muon's essence perfectly. It's essentially an electron that got too ambitious, carrying the same negative charge but weighing about 207 times more. It doesn't stick around long either, decaying into other particles in just 2.2 microseconds. For decades, the muon seemed like nature's prank, a redundant particle with no obvious purpose, tolerated by theorists but rarely celebrated. And then the wobble changed everything. You've probably experienced wobbling in your own life. A spinning top losing its balance, a bicycle wheel oscillating before you correct course. In the quantum world, particles wobble too, but in a much stranger sense. Every charged particle acts like a tiny magnet, spinning on its axis and generating a magnetic field. This magnetic moment, as physicists call it, determines how the particle interacts with external magnetic fields. For a classical spinning sphere, you could calculate this value using straightforward equations. But particles aren't classical spheres. They're quantum mechanical entities that exist in a haze of probability and virtual interactions. Here's where things get mind-bending. Empty space, according to quantum mechanics, isn't really empty at all. It seethes with virtual particles popping in and out of existence, borrowed from the vacuum's energy budget for a fleeting instance before annihilating back into nothing. When a muon moves through space, it interacts with this quantum foam. Virtual photons, virtual quarks, virtual everything. They all contribute tiny corrections to the muon's magnetic moment, causing it to wobble slightly more than a naive calculation would predict. The standard model accounts for these contributions with extraordinary precision, summing up millions of quantum interactions to produce a prediction accurate to better than 1 part in a billion. The experiments to measure this wobble are themselves monuments to human ingenuity. At Fermilab, just outside Chicago, scientists built a ring 50 feet in diameter, filled with a magnetic field more uniform than perhaps any other large-scale magnetic field ever created on Earth. Muons enter this ring travelling at nearly the speed of light, circling around and around while their magnetic moments wobble against the field. Detectors positioned around the ring measure precisely when and where each muon decays, and from millions of these measurements, physicists can reconstruct exactly how much the muons wobbled during their brief lives. The result, announced with great fanfare in 2021 and confirmed with additional data since then, shows that muons wobble slightly more than the standard model predicts. The discrepancy is tiny in absolute terms, a difference in the 11th decimal place, but it's persistent and statistically significant. In particle physics, when your measurement differs from theory by more than 5 standard deviations, you've found something real. The muon anomaly hovers tantalizingly close to that threshold, and recent results from CERN's own experiments have only strengthened the case that something genuinely strange is happening. Historians still argue whether the muon anomaly represents the first crack in the standard model or merely an unresolved computational challenge. The theoretical prediction requires calculating contributions from an incredibly complex process called hadronic vacuum polarization, where virtual quarks and gluons briefly appear in the vacuum and affect the muon's wobble. These calculations are notoriously difficult, and different methods yield slightly different answers. Some physicists believe the discrepancy will vanish once theorists sort out their calculations. Others are convinced that no amount of computational refinement will make the anomaly disappear, and that new physics is the only explanation. Here's a quirky detail that captures the obsessive precision of this work. The muon's magnetic moment is often expressed as a number called G2, representing how much the actual value differs from a simple prediction. The experimental value of G2 has been measured to about 11 significant figures, making it one of the most precisely measured quantities in all of science. If the discrepancy is real, it means our understanding of the quantum vacuum, the supposedly empty space that permeates everything, is fundamentally incomplete. You find yourself standing before one of CERN's detector displays, watching simulated muon tracks spiral through magnetic fields like ghostly ribbons. Each track represents a particle that existed for less than a millionth of a second, yet carried within its brief existence evidence of something beyond current physics. The muon doesn't care about our theories or our expectations. It simply wobbles according to whatever laws actually govern the universe, laws that we apparently don't fully understand yet. What could cause the extra wobble? The possibilities make physicists' hearts race with equal parts excitement and anxiety. Perhaps there are new particles, too heavy to create directly in colliders, but light enough to contribute as virtual fluctuations in the quantum vacuum. Perhaps the forces we know about, electromagnetism, the weak force, the strong force, are not the complete picture, and additional forces exist that only manifest at scales we haven't yet probed. Perhaps the muon is a messenger from a realm of physics we haven't even imagined, carrying information about particles and symmetries that lie beyond the standard model's horizon. The most tantalizing aspect of the muon anomaly is how perfectly it aligns with other unexpected results from CERN and elsewhere. If the muon were the only particle misbehaving, you might dismiss it as an isolated puzzle, interesting but not earth-shattering. But the muon's wobble exists alongside strange beauty quark decays, unexpected neutrino behaviour, and a host of other small deviations that all seem to point in the same direction, toward new physics lurking just beyond our current experimental reach. You watch another batch of data scroll across the screen, numbers that represent millions of muon decays analysed with algorithms refined over decades of effort. Somewhere in those numbers, evidence of new particles might be hiding, waiting for the statistical significance to cross the threshold into certainty. The physicists working on these experiments have dedicated their careers to this search, knowing full well that nature might refuse to cooperate, that the anomaly might evaporate with better measurements, that they might spend years chasing a statistical ghost. But they also know that history rewards the patient and the persistent. Every major discovery in physics has been preceded by anomalies that refuse to go away, by tiny discrepancies that eventually blossomed into revolutions. The muon's wobble might be nothing, or it might be the first tremor of a scientific earthquake that will reshape our understanding of reality itself. The soft hum of cooling systems fills the air as you move deeper into the facility, leaving the muon's mysteries behind for now, but carrying with you the unsettling knowledge that empty space itself might be hiding secrets we've only begun to glimpse. Beauty quarks don't actually care about aesthetics, despite their glamorous name. They earned the moniker back in 1977, when physicists at Fermilab discovered them, part of a whimsical tradition of giving particles evocative names. You have up quarks and down quarks forming ordinary matter, charm and strange quarks adding complexity, and at the heaviest end, top and bottom quarks. The bottom quark got nicknamed Beauty by some researchers, and the name stuck in certain circles, lending an air of elegance to what is ultimately just another point-like particle governed by quantum mechanics. But here at CERN, beauty quarks have become protagonists in one of the most intriguing scientific dramas of the 21st century. The LHCb detector sits at one of the 4 collision points around the Large Hadron Collider ring, and unlike its more famous siblings ATLAS and CMS, it wasn't designed to discover new particles directly. Instead, LHCb specializes in precision measurements of how particles decay, the specific ways in which heavy particles transform into lighter ones, releasing energy and producing cascades of secondary particles that spray outward like subatomic fireworks. For beauty quarks, these decays follow patterns that the standard model predicts with remarkable precision. At least, they're supposed to. You walk through the LHCb control room, past screens displaying decay diagrams and statistical analyses, and you begin to understand why the results from this experiment have sent tremors through the physics community. When a beauty quark decays, it can produce various combinations of lighter particles. One particularly important decay mode involves the beauty quark transforming and eventually producing either an electron-positron pair or a muon-antimuon pair. According to the standard model, these two outcomes should happen at essentially the same rate, differing by only tiny corrections related to the mass difference between electrons and muons. This principle is called lepton universality, the idea that the fundamental forces treat electrons, muons and tau particles identically, distinguishing between them only through their different masses. Lepton universality isn't just a convenient assumption, it's baked into the mathematical structure of the standard model at the deepest level. The equations describing electroweak interactions are written to treat all leptons symmetrically. If you found evidence that this symmetry was broken, you wouldn't just be finding a new particle or a new force, you'd be discovering that one of the foundational principles of modern physics is wrong. The LHCb collaboration has now accumulated years of data from billions of beauty quark decays, and the pattern that emerges is troubling. The ratio of muon-producing decays to electron-producing decays doesn't quite match the standard model prediction. The discrepancy isn't huge, it's subtle, hovering at the edges of statistical significance, but it's persistent. Different analyses, different data sets, different methodological approaches all seem to converge on the same uncomfortable conclusion. beauty quarks are treating electrons and muons differently, in violation of a principle that physics has relied upon for half a century. Historians still argue whether the first hints of lepton universality violation appeared in earlier experiments, or whether LHCb's precision measurements were truly the pioneering discovery. What's certain is that the implications are staggering. If leptons are not universal, if the forces of nature genuinely distinguish between an electron and a muon in ways beyond their mass difference, then something new must exist to cause this distinction. Perhaps a new particle, one that couples differently to different leptons. Perhaps a new force, operating at scales just beyond our current experiments. Perhaps the entire framework of electroweak unification, one of the greatest achievements of 20th century physics, needs revision. Here's a quirky detail that illustrates the difficulty of this work. Measuring the ratio of muon to electron decays requires exquisite control over systematic uncertainties. Electrons and muons leave different signatures in detectors. Electrons create electromagnetic showers, while muons punch through material like ghosts, and any imperfection in understanding these differences could produce a fake signal. The LHCb team has spent years hunting down every possible source of systematic error, redesigning analyses, cross-checking with independent methods. The fact that the anomaly survives this scrutiny gives it weight. You pause before a display showing the decay of a meson, a particle containing a beauty quark paired with another quark. The animation shows the particle's trajectory through the detector, its eventual decay point marked with a yellow star, and the resulting products spraying outward along curved paths bent by magnetic fields. Each of these decays is a tiny experiment, a measurement of whether nature respects lepton universality or violates it. Accumulated over billions of collisions, these experiments speak with collective authority that individual measurements never could. The physics community's reaction to the beauty quark anomalies has been a fascinating mixture of excitement and caution. Senior physicists who remember previous anomalies that evaporated with better statistics urge patience and skepticism. Younger researchers, eager for the breakthrough that could define their careers, analyze the data from every conceivable angle, searching for confirmation or refutation. Theorists have already published hundreds of papers proposing explanations for the anomaly, each one involving new particles or new forces that might restore lepton universality while explaining the observed violation. The most popular candidates include particles called leptoquarks, hypothetical entities that could connect quarks and leptons in ways the standard model doesn't allow, and extended gauge symmetries that add new force-carrying particles to the mix. What makes the beauty quark anomaly particularly compelling is how it connects with the muon wobble you encountered earlier. Both anomalies involve muons behaving differently than expected. Both suggest that new physics preferentially couples to the heavier leptons. This pattern, if it holds, would provide crucial clues about what lies beyond the standard model. Random fluctuations don't produce coherent patterns. New physics does. The afternoon light never penetrates this far underground, but the glow of computer screens creates its own artificial day, one where time is measured not in hours, but in integrated luminosity, the total number of collisions accumulated by the experiments. More luminosity means more data, more precision, more power to distinguish genuine signals from statistical noise. The LHCb detector is currently being upgraded to handle even higher collision rates, promising a flood of new beauty quark decays that could finally settle the question. You move away from the displays, carrying with you the image of those decay diagrams, each one a tiny window into the fundamental structure of reality. Beauty quarks may have earned their name through arbitrary whimsy, but they now carry a burden of profound significance, their decays potentially holding the key to physics beyond our current understanding. Neutrinos are perhaps the universe's most antisocial particles, and that's saying something in a world where dark matter refuses to interact with light at all. You've been hearing about them since early in our journey, but now it's time to meet them properly. These ghost particles that stream through your body by the trillions every second without disturbing a single atom. The sun produces them in nuclear fusion reactions. Radioactive decay produces them. Even the banana sitting on your kitchen counter produces them, thanks to the potassium-40 in its flesh. And here at CERN, scientists have been producing them deliberately, studying them obsessively, and recently, counting more of them than their equations say should exist. The neutrino's ghostly nature comes from its near-complete indifference to ordinary matter. While electrons and quarks interact through electromagnetism and the strong force, neutrinos respond only to the weak nuclear force, the feeblest of nature's fundamental interactions. This makes them extraordinarily difficult to detect. A neutrino produced in the sun's core will typically pass through the entire Earth without hitting a single atom. To catch even a handful requires building detectors the size of skyscrapers, filling underground caverns with thousands of tons of water or liquid argon, and waiting patiently for years while neutrinos occasionally condescend to interact. The standard model includes 3 types of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino, each one paired with its corresponding charged lepton. For decades, physicists believed neutrinos were massless, particles of pure energy that zip through the cosmos at the speed of light, leaving no trace of their passage. This assumption was overturned in the late 1990s when experiments in Japan and elsewhere discovered that neutrinos oscillate, transforming from one type to another as they travel. This oscillation requires the neutrino types to have slightly different masses, and masses require the standard model to be extended in ways that physicists are still working to understand. Here's where the surplus comes in. Experiments at CERN and other facilities have been meticulously counting neutrinos produced in particle collisions, comparing the numbers to theoretical predictions. These predictions account for all the ways neutrinos can be produced, all the ways they can oscillate between types during their journey to the detector, and all the efficiency factors of the detection process itself. The calculations are fiendishly complex, involving quantum mechanical interference effects and precise knowledge of particle physics cross-sections. And yet, the numbers don't quite add up. There seem to be more neutrinos arriving at detectors than the standard model predicts should exist. Historians still argue whether the neutrino surplus represents a genuine anomaly or a misunderstanding of the complex processes involved in neutrino production and detection. The measurements come from multiple experiments using different techniques, which strengthens the case that something real is happening. But systematic uncertainties in neutrino physics are notoriously difficult to quantify. The detectors themselves are imperfect. The production mechanisms involve hadronic physics that isn't fully understood, and the oscillation parameters have their own uncertainties. Skeptics argue that cleaning up these issues will make the surplus disappear. Believers counter that independent experiments finding similar anomalies is exactly what you'd expect if the effect were genuine. The most exciting possibility is that the surplus indicates the existence of sterile neutrinos, hypothetical neutrino types that don't interact through any of the standard model forces. While ordinary neutrinos interact weakly, sterile neutrinos would interact not at all, communicating with the observable universe only through gravity and through mixing with their active cousins. If sterile neutrinos exist, the 3 known neutrino types would occasionally transform into sterile states during their oscillations, then transform back. This would produce exactly the kind of surplus and deficit patterns that experiments have been observing. Here's a quirky detail that captures the strange world of neutrino physics. Because neutrinos interact so rarely, detecting them requires extraordinarily pure materials. Any radioactive contamination in a detector would produce background signals that swamp the rare neutrino interactions you're trying to measure. Some neutrino experiments use copper that has been stored deep underground for decades, allowing cosmic ray-induced radioactivity to decay away. Others use water purified to levels far beyond anything needed for drinking. 1 part per quintillion of uranium or thorium can ruin an experiment. You imagine the neutrinos streaming through the rock above you right now, born in the sun 8 minutes ago, or in distant supernova millions of years ago, passing through the Swiss Alps and the CERN facility, and your own body without acknowledging any of it. Each neutrino carries information about its origin, encoded in its energy and flavour, but extracting that information requires catching it first, a task of almost absurd difficulty given how reluctant neutrinos are to be caught. The implications of sterile neutrinos extend far beyond particle physics. In cosmology, sterile neutrinos are candidates for dark matter, the invisible substance that holds galaxies together. If they have the right mass and mixing properties, sterile neutrinos could have been produced in the early universe in just the quantities needed to explain dark matter observations. This would be an elegant solution to 2 problems at once: explaining the neutrino surplus and identifying the nature of dark matter, though nature rarely cooperates with our hopes for elegance. Some theorists have proposed even more exotic explanations for the neutrino anomalies. Perhaps neutrinos are slipping into extra dimensions, disappearing from our 3-dimensional world and reappearing elsewhere. Perhaps they're decaying into particles we haven't yet discovered. Perhaps the oscillation equations themselves need modification, with additional terms that current experiments haven't fully accounted for. Each possibility opens new avenues for exploration and new predictions that future experiments could test. You stand near one of CERN's neutrino beam facilities, where protons smash into targets to produce cascades of particles that eventually decay into neutrinos. The beam is aimed toward detectors hundreds of kilometers away, shooting through the Earth's crust like an arrow of ghosts. By the time the neutrinos reach those distant detectors, most will have passed through without interacting, but a precious few will collide with atomic nuclei and reveal their presence. Counting those collisions, comparing them to predictions, searching for anomalies, this is the painstaking work of neutrino physics. The ghost particles don't care about your curiosity. They continue their silent passage, indifferent to the questions you ask and the theories you construct. But in their indifference lies information, patterns that could reveal whether our universe contains hidden particles, hidden dimensions, or simply hidden complexities in processes we thought we understood. You exist, and that's profoundly strange. Not philosophically strange, though that too, but physically strange. A puzzle that has haunted physicists since the early days of particle physics, and that CERN's recent findings have made even more acute. The universe should have annihilated itself shortly after the Big Bang, matter and antimatter cancelling each other in a flash of pure energy, leaving behind nothing but radiation. Yet here you are, made of matter, reading these words on a device made of matter, on a planet made of matter, in a universe that is overwhelmingly material despite every indication that it should be empty. This is the antimatter mystery, and CERN has been probing it with instruments of extraordinary precision, finding clues that deepen the puzzle rather than resolve it. Antimatter isn't science fiction, it's science fact, produced routinely in particle accelerators and occasionally encountered in natural processes like radioactive decay and cosmic ray interactions. An anti-electron, called a positron, has the same mass as an electron but opposite charge. An antiproton has the same mass as a proton but negative instead of positive charge. When a particle meets its antiparticle, they annihilate each other completely. converting their mass into energy according to Einstein's famous equation. This isn't theoretical. It's been observed millions of times in laboratories around the world, each annihilation releasing a burst of gamma rays that detectors can measure with exquisite accuracy. The Standard Model treats matter and antimatter with almost perfect symmetry. The equations that govern particle interactions work nearly the same if you replace every particle with its antiparticle and flip a few signs. This symmetry, combined with reasonable assumptions about the early universe, predicts that the Big Bang should have produced equal amounts of matter and antimatter. They should have annihilated each other in the first moments of cosmic history, leaving behind a universe empty of everything except photons. The fact that matter survived, that there's something rather than nothing, requires an asymmetry, a slight preference for matter over antimatter that the Standard Model struggles to explain. Physicists call this the baryon asymmetry problem, and it's one of the biggest unsolved questions in cosmology. Something must have tipped the balance in favour of matter, some process or property that treated particles and antiparticles slightly differently, allowing a tiny fraction of matter to survive the Great Annihilation. The Standard Model contains mechanisms that could contribute to this asymmetry. Subtle differences in how certain particles decay, known as CP violation, but the effects are far too small to account for the matter we observe. The universe requires a much bigger push than current physics can provide, and that push must come from somewhere beyond our current understanding. Here's where CERN enters the picture with particular relevance. The experiments at the Large Hadron Collider have been studying antimatter with unprecedented precision, searching for differences between matter and antimatter that might explain how the universe survived its infancy. The Alpha experiment, for instance, has trapped antihydrogen atoms, each one consisting of an antiproton orbited by a positron, and measured their properties with extraordinary accuracy. These trapped antiatoms hover in magnetic bottles, suspended in vacuum, isolated from ordinary matter that would annihilate them instantly. Scientists have measured their spectral lines, their response to gravity, their behaviour in magnetic fields, searching for any deviation from what ordinary hydrogen would show. Historians still argue whether the baryon asymmetry will be solved by new particles, new forces, or modifications to our understanding of the early universe. Some physicists believe the answer lies in the neutrino sector, where CP violation might be much larger than in quark interactions. The neutrinos you encountered earlier, those ghost particles streaming through everything, might hold the key to why matter exists. Others propose exotic mechanisms involving hypothetical particles that existed only in the extreme conditions of the early universe, particles too heavy to create in any laboratory, but influential in the cosmic dawn. Still, others suggest that our understanding of the Big Bang itself might need revision, perhaps involving multiple phases or unusual cosmological dynamics that created a symmetry through mechanisms we haven't yet conceived. Here's a quirky detail that might make you smile. Antimatter is extraordinarily expensive to produce. If you wanted to buy enough antihydrogen to power a science fiction spacecraft, you'd need to spend roughly $60 trillion per gram, based on current production costs. CERN produces only billionths of a gram per year, barely enough for precision experiments, nowhere near enough for practical applications. The antimatter drives of Star Trek remain firmly in the realm of fiction, not because the physics is wrong, but because the economics are impossible. Antimatter remains a tool for fundamental research rather than a technology. Its annihilating power locked away by the sheer difficulty of making and storing it. The measurements at CERN have found that antihydrogen atoms respond to gravity in the same way as ordinary hydrogen. They fall down, not up, contrary to some speculative theories that antimatter might experience anti-gravity. This result, published with great fanfare, eliminates one exotic possibility but leaves the fundamental asymmetry unexplained. If antimatter falls just like matter, if it responds to forces just like matter, if it has the same mass and the same spectral properties as matter, then why did matter win the cosmic lottery? The question remains open, a reminder that the existence of the universe itself is not fully understood by our best theories. What connects this to the anomalies we've been discussing throughout our journey? The muon wobble, the beauty quark decays, the neutrino surplus. All of these point toward new physics beyond the standard model. And new physics typically brings new sources of CP violation, new ways for the universe to distinguish between matter and antimatter. If CERN discovers the particles or forces responsible for the current anomalies, those same discoveries might finally explain why matter won its ancient battle against antimatter. The connections aren't guaranteed, but they're tantalizing, threads that might weave together into a coherent tapestry of understanding. You wander through the antimatter research area in your imagination, past equipment designed to slow down antiprotons, trap them in magnetic fields, and combine them with positrons to form antihydrogen. The process requires temperatures colder than outer space, just a fraction of a degree above absolute zero, a magnetic containment so precise that a single error would allow the antimatter to touch ordinary matter and annihilate in a flash of gamma radiation. The physicists working here handle substances that could, in sufficient quantity, release more energy than nuclear weapons, yet they do so with the calm methodicalness of professionals who have long since moved past the science fiction glamour to focus on the actual science. The asymmetry between matter and antimatter is ultimately an asymmetry in the laws of physics themselves. Something in the fundamental rules governing the universe treats particles and antiparticles slightly differently, and that something allowed you to exist. Every atom in your body, every star in the sky, every galaxy spinning through the cosmic void, all of it traces back to that primordial imbalance, that tiny preference for matter that the standard model cannot explain. You are, quite literally, the product of a cosmic asymmetry, a violation of symmetry that physics doesn't yet understand. As you move deeper into CERN's underground labyrinth, the antimatter puzzle stays with you like a persistent question. The universe's existence is not guaranteed by physics as we understand it. Something beyond our current theories made it possible, and finding that something is one of the great quests of modern science. The anomalies at CERN might be breadcrumbs on the trail toward that understanding, hints that new physics awaits discovery. Physics that could finally explain the most fundamental fact of all, that anything exists rather than nothing. The hum of machinery continues around you, detectors recording collisions, computers processing data, physicists analysing results. Somewhere in all this activity, the answer to the antimatter mystery might already be hiding, waiting for someone to recognise it among the trillions of recorded events. The search continues, patient and persistent, driven by the profound strangeness of your own existence. Dark matter has been haunting astronomy for nearly a century, an invisible presence that reveals itself only through gravity, and now CERN's anomalies might finally be giving it a face. You've heard the term before, dark matter, perhaps imagined it as something mysterious and sinister lurking in the void between stars. The reality is both more mundane and more profound. Dark matter is simply matter that doesn't emit, absorb or reflect light, making it invisible to telescopes but utterly real in its gravitational effects on visible matter. It's the cosmic equivalent of feeling someone's presence in a dark room. You can't see them, but you know they're there from the way the floorboards creak beneath their feet. The evidence for dark matter comes from multiple independent observations, each one pointing to the same invisible elephant in the cosmic room. Galaxies rotate faster at their edges than they should if only visible matter were present. Suggesting invisible mass in their halos provides additional gravitational pull. galaxy clusters bend light from distant objects more strongly than their visible mass would predict, acting as gravitational lenses that reveal hidden mass through Einstein's relativity. The cosmic microwave background radiation, the afterglow of the Big Bang itself, contains patterns that require dark matter to explain, temperature fluctuations that match theoretical predictions only when dark matter is included. The large-scale structure of the universe, the filaments and voids that galaxies trace across cosmic distances, matches simulations only when dark matter is included as the invisible scaffolding on which visible matter accumulated. Each piece of evidence independently points to the same conclusion. Roughly 85% of the matter in the universe is dark, invisible, and utterly unknown. This isn't a small correction to our understanding. It's a fundamental revelation that most of what exists in the universe has been hiding from us since the beginning of astronomical observation. Every galaxy you've ever seen in photographs, every star chart, every cosmic map, they all show only the tip of the iceberg, the luminous minority floating on an ocean of darkness. The Standard Model contains no particle that could be dark matter. Every particle it describes either interacts with light or decays too quickly to survive from the early universe until today. If dark matter exists, and the astronomical evidence overwhelmingly suggests it does, then physics must be extended to include new particles with properties the Standard Model doesn't allow. This is where the anomalies at CERN become genuinely exciting. The same new physics that explains the muon wobble and beauty quark decays might also provide dark matter candidates. The cracks in particle physics might open windows onto cosmology. Historians still argue whether dark matter will turn out to be a single particle species or a complex dark sector containing multiple types of particles with their own interactions. The simplest models propose a single weakly interacting massive particle, or WIMP, that feels gravity and perhaps the weak nuclear force but nothing else. These WIMPs would have been produced in the early universe, would have survived until today because they have nothing to decay into, and would now permeate every galaxy including our own. Trillions of WIMPs might be passing through your body right now, utterly oblivious to the atoms that compose you, interacting so rarely that decades of experiments have detected nothing. More elaborate models imagine dark atoms, dark photons, even dark life forms, entire realms of complexity invisible to our instruments, but fully real nonetheless. The dark sector might be as rich and varied as the visible sector, with its own forces, its own chemistry, its own structures. This is highly speculative, of course, but it's worth contemplating the possibility that the universe contains whole categories of complexity that we've never glimpsed and might never directly observe. Here's a quirky detail that captures the challenge of dark matter detection. Experiments searching for WIMPs use detectors buried deep underground, shielded from cosmic rays and radioactive backgrounds by kilometers of rock, cooled to near absolute zero, and equipped with sensors capable of detecting the recoil of a single atomic nucleus. If a dark matter particle collides with an atomic nucleus in the detector, an event expected to happen perhaps once per year in a ton of detector material, the nucleus would recoil slightly, producing a tiny signal that the sensors could potentially detect. After decades of searching with increasingly sensitive detectors, these experiments have found nothing. Either dark matter particles interact even more weakly than WIMPs were expected to, or dark matter is something completely different from what theorists predicted. The anomalies at CERN offer a potential breakthrough in this frustrating search. If new particles exist that couple preferentially to muons, as the muon wobble and beauty quark results suggest, these particles might also couple to dark matter. The connection isn't guaranteed, but it's tantalizing. Theories that explain the CERN anomalies often predict additional particles that could serve as dark matter candidates, linking two of the biggest mysteries in physics through a single extension of the standard model. Finding one might lead to finding the other. You pause before a display showing the dark matter distribution in a simulated galaxy cluster, the invisible mass mapped through gravitational lensing observations. The image looks like a cosmic web, filaments of darkness connecting bright nodes of visible galaxies, the whole structure resembling neurons in a vast cosmic brain. This is the scaffolding on which the universe was built, the invisible framework that guided the formation of everything you can see in the night sky. And somewhere in CERN's data, clues to the nature of this framework might be hiding among the millions of recorded collisions. The search for dark matter at CERN takes several forms. Direct production attempts to create dark matter particles in collisions, looking for events where energy and momentum go missing because invisible particles carry them away. These missing energy searches have so far found nothing beyond what the standard model predicts, but they've set limits on what dark matter can be. Precision measurements, like those revealing the muon anomaly, search for the indirect influence of dark matter on known processes, looking for subtle shifts in particle properties that might reveal dark contributions. Both approaches continue, driven by the conviction that dark matter must eventually reveal itself. One particularly elegant possibility involves particles called axions, originally proposed to solve a different problem in physics: why the strong nuclear force doesn't violate certain symmetries it theoretically could. Axions would be extremely light and extremely weakly interacting, making them difficult to produce in colliders, but potentially detectable through other means. Some theorists believe axions could be produced in the quantum fluctuations that contribute to the muon's wobble, providing a connection between the CERN anomaly and the dark matter puzzle. The axion remains hypothetical, but experiments designed specifically to detect it are operating and improving. The underground chambers of CERN seem fitting for contemplating dark matter. These tunnels carved through ancient rock, lit by artificial light, isolated from the cosmic ray background that constantly bombards the surface. Dark matter passes through here too, of course. Millions of dark matter particles streaming through every square centimetre every second if the theories are correct. But they pass without interacting, ghostly visitors from the invisible majority of the universe. The detectors designed to catch visible particles are blind to this dark flux, recording only the luminous minority while the dark majority slips through unnoticed. What would it mean to finally identify dark matter? Beyond satisfying scientific curiosity, it would represent a fundamental expansion of our understanding of nature. We would have discovered that the universe contains more types of stuff than we previously knew. An entire category of matter that has shaped cosmic evolution without ever being directly observed. The standard model would need updating, textbooks would need rewriting, and physicists would have new mysteries to explore. What properties does dark matter have? How did it form? What role does it play in the universe's ultimate fate? Supersymmetry was supposed to save physics. For decades, it stood as the most promising framework for extending the standard model, a mathematically elegant theory that solved multiple problems simultaneously and predicted a whole zoo of new particles waiting to be discovered at CERN. Yet here you stand, in the facility that was supposed to vindicate supersymmetry, and the theory is on life support, its most natural predictions stubbornly refusing to materialize. The anomalies we've been discussing might be its last hope, or they might drive the final nail into its coffin, ending one of the most beautiful dreams in theoretical physics. The idea behind supersymmetry is beautiful in the way that physics ideas sometimes are, a perfect symmetry linking two different types of particles. Fermions, particles like electrons and quarks that make up matter, would be paired with bosons, particles like photons and gluons that carry forces. Every fermion would have a boson partner, and every boson would have a fermion partner, the two related by a mathematical transformation that exchanges their fundamental properties. The electron would have a supersymmetric partner called the selectron, carrying the same charge but with different spin. The photon would have a photino, a fermionic version of light itself. The Higgs boson would have a Higgsino, and so on through the entire particle zoo, doubling its population in one elegant stroke. This symmetry isn't just aesthetic, it solves real problems that plague the standard model. Remember the hierarchy problem from earlier in our journey. The puzzle of why the Higgs boson's mass is so much smaller than quantum fluctuations would naturally make it. Supersymmetry provides a natural, automatic solution. The contributions from ordinary particles that would drive the Higgs mass to enormous values are exactly cancelled by contributions from their supersymmetric partners. Every fermion loop that pushes the mass up is balanced by a boson loop that pulls it down, and vice versa. The balance is automatic, a consequence of the symmetry itself, requiring no fine-tuning of parameters, no suspicious coincidences, no anthropic selection effects. Supersymmetry also provides dark matter candidates, addressing another mystery we've been exploring. The lightest supersymmetric particle, in many versions of the theory, would be stable, unable to decay into anything lighter, because there's nothing lighter it could decay into while conserving the theory's symmetries. This particle, called the neutralino in some models, would interact weakly with ordinary matter, persist from the early universe until today, and account for the dark matter that astronomers observe through gravitational effects. The neutralino would be a WIMP of exactly the type dark matter searchers have been looking for, produced in the Big Bang, surviving for billions of years, now pervading every galaxy. Two birds, one stone, the hierarchy problem and dark matter, both addressed by a single beautiful symmetry. Historians still argue whether supersymmetry's appeal was always more mathematical than physical, or whether the community genuinely expected the particles to appear at the energies CERN could reach. The optimistic predictions made in the 1980s and 90s place supersymmetric particles just above the reach of previous accelerators, tantalizingly close to discovery. The logic seemed compelling. If supersymmetry solves the hierarchy problem naturally, the supersymmetric partners should have masses not too different from the Higgs boson's mass, putting them within reach of the Large Hadron Collider. When the LHC began operations in 2008, supersymmetry enthusiasts expected confirmations within years, Nobel Prizes within a decade. Instead, the years have passed, the collisions have accumulated, and the supersymmetric partners remain absent. The searches have been comprehensive and creative, looking for every possible signature that supersymmetric particles might produce. Cascades of decays that would produce multiple jets and missing energy. Distinctive patterns of particles that couldn't arise from standard model processes. Long-lived particles that would travel through the detector before decaying. Nothing. The simplest, most natural versions of supersymmetry, the ones that most elegantly solve the problems they were designed to solve, have been ruled out by the data. Here's a quirky detail that captures the current mood in the field. Physics conferences used to feature sessions titled Supersymmetry Searches, with standing room only audiences, every seat filled with physicists eager to hear about the latest results, anticipating the announcement that would change everything. Today, those sessions are smaller, quieter, dominated by null results and increasingly exotic models designed to explain why the particles haven't appeared yet. The buzz has faded. The optimism has curdled into something more measured, more cautious, more pessimistic. Some physicists have moved on entirely, directing their energies toward other problems. The most natural versions of supersymmetry predicted particles with masses around a few 100 billion electron volts, easily within the LHC's reach. Those versions are now excluded. What remains are more complicated variants, models where the supersymmetric particles are heavier than expected, or where they decay in unusual ways that current searches might miss, or where the spectrum of masses is compressed so that the visible decay products carry too little energy to distinguish from background. These surviving models have more parameters, less predictive power, and a growing sense of desperation about them, like a theory retreating into corners to avoid the encroaching data. The anomalies at CERN offer supersymmetry an unexpected lifeline, a potential resurrection from what many considered its deathbed. The muon wobble and beauty quark decays, if they're real signals of new physics, could be explained by supersymmetric particles with specific properties. Perhaps the supersymmetric partners aren't where we expected them to be. Perhaps they have unusual couplings that enhance their effects on certain processes while making them hard to produce directly in collisions. Theorists have been busy constructing supersymmetric models that explain the anomalies, and some of these models make predictions that future experiments could test, offering a path toward either confirmation or final refutation. But the anomalies are a double-edged sword for supersymmetry. If they're explained by new particles that aren't supersymmetric, by leptoquarks, or extended gauge symmetries, or something even more exotic, then supersymmetry loses its primary motivation. Why believe in a beautiful but undetected symmetry when a different, less elegant framework actually explains the data? The pragmatic answer is that you shouldn't, that beauty alone cannot sustain a physical theory, that ultimately nature decides what's real regardless of what mathematicians find appealing. The next few years might decide whether supersymmetry remains a viable theory or becomes a historical footnote, a beautiful idea that nature chose not to implement. You walk past posters showing the detector signatures that supersymmetric particles would produce if they existed. Missing energy events, cascades of particles, distinctive patterns that haven't been observed despite billions of collisions analysed with sophisticated algorithms. The absence of evidence isn't evidence of absence, the optimists insist, but it becomes harder to maintain that position with each negative result. At some point, the theory's parameters must be pushed into corners so remote that the theory loses its explanatory power, becoming a just-so story rather than a predictive framework. The emotional stakes for physicists shouldn't be underestimated. Careers have been built on supersymmetry. Graduate students chose advisors based on their work in supersymmetric phenomenology. Tenure cases were argued on the basis of contributions to supersymmetric model building. Entire research groups organised themselves around the expectation that supersymmetry would be discovered, that the next generation of physicists would spend their careers exploring its implications. If the theory fades, an entire generation of physicists will need to reinvent themselves, finding new problems to work on, new frameworks to develop, new hopes to nurture. Yet science ultimately cares only about what nature says, not what physicists hope. If supersymmetry is real, evidence will eventually appear, perhaps at higher energies than we've yet probed, perhaps in precision measurements that reveal its subtle influence. If it isn't, no amount of mathematical elegance will save it. No wishful thinking will make particles appear that don't exist. The anomalies at CERN have given both sides new ammunition, new arguments, new analyses. The debate continues, fiercer and more consequential than ever. Extra dimensions sound like science fiction, the territory of wormholes and parallel worlds and spacecraft folding space to travel faster than light. But in the serious corridors of theoretical physics, extra dimensions are mathematical necessities for certain theories and genuine possibilities for experimental exploration. And the anomalies at CERN might be particles leaking in and out of dimensions you cannot see, slipping through the cracks in three-dimensional reality into geometries that extend beyond human perception. The idea that space might have more than 3 dimensions dates back over a century, to the work of Theodor Kaluza and Oskar Klein in the 1920s. They noticed something remarkable. Adding a 4th spatial dimension, compactified, rolled up so small you couldn't see it, allowed gravity and electromagnetism to be unified into a single geometric framework. In 4 spatial dimensions plus 1 time dimension, what appears as electromagnetism in our ordinary 3-dimensional experience could actually be a manifestation of higher dimensional gravity. The mathematics was elegant, suggesting that the fundamental forces might be aspects of geometry rather than separate phenomena. For decades, extra dimensions languished as a theoretical curiosity, occasionally resurrected by ambitious theorists but never mainstream, never taken as seriously as other approaches to unification. The dimensions would need to be incredibly small to have escaped detection, and the motivation for introducing them seemed insufficient compared to the conceptual cost of abandoning our intuitive understanding of space. String theory changed that calculation dramatically. In the 1980s, physicists realized that string theory, a framework where fundamental particles are actually tiny vibrating strings rather than point-like objects, requires extra dimensions to be mathematically consistent. The requirement isn't optional. The theory simply doesn't work in 3 spatial dimensions. The strings must vibrate in a higher dimensional space, specifically 9 spatial dimensions plus 1 time dimension, for the mathematics to make sense. This sounds absurd at first, like a theory demanding too much, but string theorists argue that the extra dimensions are as real as the 3 we perceive. We simply can't access them directly because they're curled up at scales far smaller than anything we can probe. The anomalies at CERN become relevant because extra dimensions could leak. Particles or energy might escape our familiar 3-dimensional world and travel through the additional dimensions before returning, or not returning at all. If this happens, experiments would observe energy disappearing, momentum going missing, particles behaving as if invisible partners were participating in reactions that we only partially observe. The missing energy signatures that CERN looks for in dark matter searches could equally well be signatures of extra dimensions, gravitons slipping away into the bulk while we're confined to the brain. Historians still argue whether extra dimensions will ever be experimentally accessible, or whether they'll remain forever in the realm of mathematical speculation without empirical grounding. The scales at which extra dimensions are expected to manifest in conventional theories, the Planck scale, roughly 100 billion times smaller than a proton, seem impossibly remote from laboratory physics, requiring energies far beyond any accelerator we could conceivably build. But some theories propose that extra dimensions could be much larger than the Planck scale, potentially large enough to produce observable effects at the energies CERN achieves. Here's a quirky detail that makes the possibilities concrete. In theories with large extra dimensions, gravity would be diluted because gravitons, the hypothetical particles carrying gravitational force, could spread into the extra dimensions while other particles remain confined to our 3-dimensional brain, like insects walking on a sheet of paper suspended in a 3-dimensional room. This dilution might explain why gravity is so much weaker than the other fundamental forces, a puzzle called the hierarchy problem that we've encountered before. The same mechanism might produce microscopic black holes in particle collisions, tiny gravitational singularities that would evaporate almost instantly through Hawking radiation, producing distinctive sprays of particles that detectors could potentially identify. The searches for microscopic black holes at CERN have so far found nothing, setting limits on the scenarios that would produce them. If extra dimensions were large enough and gravity strong enough at small scales, black holes should have appeared by now. Their absence constrains the parameter space for extra-dimensional theories, but doesn't eliminate them entirely. the dimensions might be smaller than the optimistic prediction suggested, or the scenarios might be more complicated than the simple models assumed. You imagine the collision point in the Large Hadron Collider, particles smashing together with energies concentrated in spaces smaller than atomic nuclei. If extra dimensions exist, some of that energy might ripple outward into spatial directions you cannot perceive, creating gravitational waves in higher dimensions, generating particles that live their entire existence outside our observable universe. The thought is dizzying, a reminder that the reality we experience might be a thin slice of something vastly larger, a brain floating in a bulk we cannot directly access. The muon wobble and beauty quark anomalies could connect to extra dimensions in several ways that theorists have explored. New particles living in the extra dimensions could contribute to quantum corrections, affecting how muons wobble and how quarks decay. The specific patterns of the anomalies, the preference for heavier leptons, the violation of universality, might be explained by geometric features of the extra-dimensional space. Different particle types might be localized in different regions of the extra dimensions, naturally producing the non-universal effects that experiments observe without requiring fine-tuning of parameters. Some of the most creative theoretical work in recent years has explored connections between extra dimensions and dark matter. Particles that can move in the extra dimensions might have different effective masses in different regions of the higher dimensional space, behaving as ordinary matter in some circumstances and as dark matter in others. The Kaluza-Klein Tower, an infinite sequence of increasingly heavy particles that appear when a dimension is compactified, might include dark matter candidates that have eluded detection because they interact so weakly with brain-bound matter. Of course, extra dimensions remain highly speculative, more mathematical possibility than established physics. The evidence is indirect and ambiguous. The theories are mathematically challenging and not fully developed, and alternative explanations exist for all the observed phenomena. But the possibility is thrilling nonetheless, a reminder that our understanding of space itself might be profoundly limited. If CERN's anomalies are genuinely evidence of extra dimensions, we would learn that the universe's spatial structure is fundamentally different from what we perceive, that behind the familiar three dimensions lies a hidden geometry that shaped the forces and particles we observe. You lean against a railing overlooking one of the detector assembly areas, where engineers work on equipment designed to capture the debris of particle collisions with ever-increasing precision. Every measurement they make, every event they record, could potentially contain information about spatial dimensions beyond human perception. The detectors don't know whether the energy they're measuring comes from ordinary particles, dark matter candidates, or messengers from extra dimensions. They simply record what happens, leaving interpretation to the physicists who analyze the data with theories that may or may not correspond to reality. The search for extra dimensions at CERN has so far produced null results. No microscopic black holes, no obvious missing energy signatures that demand extra-dimensional explanations, no graviton production visible above background. But null results narrow the possibilities, constraining the parameter space where extra dimensions might hide. If the current anomalies are eventually explained by extra dimensions, it will be a version of the theory that survived this gauntlet of negative searches, a model that predicted small effects in precision measurements rather than dramatic signatures in new particle production. The Higgs boson took almost 50 years to find, a journey from theoretical prediction in 1964 to experimental confirmation in 2012. You remember the celebrations, or at least you've seen the footage, scientists weeping with joy in the CERN auditorium, champagne corks popping in offices around the world, Peter Higgs himself wiping tears from his eyes as decades of hope crystallized into discovery. It was one of physics' greatest triumphs, the discovery of the particle that gives mass to other particles the final piece of the Standard Model puzzle that had eluded searchers for half a century. And yet, even as physicists celebrated, they knew that the Higgs brought problems as well as answers, questions as well as solutions. A decade later, those problems are becoming harder to ignore. The Higgs mechanism works through a field that permeates all of space, the Higgs field, interacting with particles and giving them mass through that interaction. Unlike other fields that fluctuate around zero, the Higgs field has a non-zero value everywhere, a constant background presence that particles wade through like swimmers moving through water. Particles that interact strongly with the Higgs field experience more resistance to acceleration and therefore appear heavier. Particles that interact weakly or not at all move freely and remain light or massless. The photon doesn't interact with the Higgs field, so it remains massless and travels at the speed of light, the ultimate speed limit of the universe. The top quark interacts very strongly, giving it the largest mass of any known fundamental particle, roughly as heavy as an entire gold atom. The elegance of this mechanism earned its inventors the Nobel Prize and gave the Standard Model its crowning achievement, the explanation of how mass itself arises from a fundamental field rather than being an intrinsic property of particles. But the Higgs boson's mass is troubling in ways that physicists have struggled to resolve. It was measured at CERN to be about 125 billion electron volts, a specific number that raises profound questions. Why that number and not some other? The Standard Model doesn't predict the Higgs mass. It merely accepts whatever value experiments determine, one of those 19 free parameters that make the theory descriptive rather than explanatory. And when theorists try to calculate what the Higgs mass should be based on quantum effects, they get answers that are wildly, disastrously wrong. The problem is that the Higgs field interacts with every massive particle in the universe, and in quantum mechanics, interactions create fluctuations. Virtual particles, those fleeting entities you encountered in the discussion of muon wobbling, constantly pop into and out of existence, and each one tugs on the Higgs field, contributing to its mass. Some fluctuations push the mass up, others push it down. In a universe with only light particles, these effects might roughly cancel, leaving the Higgs mass manageable. But the universe contains the top quark, enormously heavy, creating enormous fluctuations that should drive the Higgs mass to values billions or trillions of times larger than what we observe. This is the hierarchy problem, and it's been haunting physics since long before the Higgs was discovered. The Higgs mass appears fine-tuned, balanced on a knife's edge by some unknown mechanism that current theories cannot explain. Supersymmetry was supposed to solve it. Remember those supersymmetric partners whose contributions would exactly cancel the problematic fluctuations. But supersymmetry hasn't shown up, and alternative solutions remain elusive, leaving the hierarchy problem as one of the deepest puzzles in fundamental physics. Historians still argue whether the hierarchy problem is a genuine puzzle, demanding new physics, or merely an artifact of our current theoretical framework that might dissolve with better understanding. Some physicists argue that the universe might simply be fine-tuned, that no deeper explanation exists for the Higgs mass, and we should accept it as a brute fact, one of those things that just is without further reason. Others find this philosophically unsatisfying, arguing that fine-tuning suggests either new physics we haven't discovered or selection effects like the anthropic principle, where we necessarily find ourselves in a universe compatible with our existence regardless of how improbable that universe might be. Here's a quirky detail that adds to the mystery. The measured Higgs mass places the universe in a peculiar situation called metastability. The energy of the Higgs field depends on its value according to current measurements, and there exists a deeper energy state that the universe hasn't reached yet. A lower valley in the energy landscape separated from our current location by a barrier, The universe is perched in a local minimum, stable against small disturbances but potentially unstable against large ones. A sufficiently energetic quantum fluctuation could, in principle, push a region of space into the lower energy state, creating a bubble of true vacuum that would expand at the speed of the light, destroying everything it encountered. Don't worry too much about this cosmic catastrophe. The probability is unfathomably small, the barrier is extremely high, and even if it happened, you wouldn't have time to notice before the bubble engulfed you. But the metastability of the vacuum connects to the Higgs mass in ways that physicists are still exploring. If new physics modifies the Higgs sector, it might stabilize the vacuum, eliminating the metastability and ensuring that our universe is truly stable rather than merely long-lived. The anomalies at CERN, if they're real, might be clues to this stabilization, hints of new particles or forces that affect the Higgs potential in ways that make the universe safer. You walk past the CMS and Atlas detectors in your imagination, those massive instruments that recorded the Higgs boson's first appearances in 2012, events where Higgs particles were created in proton collisions, existed for a fleeting instant, then decayed into pairs of photons or Z-bosons or other particles that the detectors could actually observe. The Higgs itself is invisible. Only its decay products reveal its presence, like footprints in snow indicating a creature you never saw. The detectors have since been upgraded, their sensitivity improved, their ability to measure Higgs properties refined through years of experience and engineering innovation. And the measurements keep revealing puzzles. The Higgs boson seems to have the properties the Standard Model predicts: its spin, its decay modes, its production rates, all matching theoretical expectations within experimental uncertainties. But small deviations might be hiding in the data, hints that the Higgs sector is more complicated than the simplest models assume. Some theories propose extended Higgs sectors with multiple Higgs bosons rather than just one, 2 Higgs doublets, or more exotic structures with charged Higgs particles and additional neutral ones. Others suggest the Higgs is not fundamental but composite, made of smaller constituents we haven't yet detected, bound together by forces we haven't yet discovered. Still others imagine the Higgs connecting to dark sectors or extra dimensions, its peculiar mass explained by geometric or dynamical effects beyond the Standard Model. Each possibility makes predictions that current or future experiments could test. Predictions about additional particles that might be produced, about deviations in Higgs properties that might become visible with more data, about rare processes that might occur at rates different from Standard Model expectations. The Higgs boson was supposed to complete the Standard Model, but instead it emphasized how much remains unexplained. Its discovery was an ending and a beginning simultaneously, the end of a search that lasted half a century, the beginning of new puzzles that might take another half-century to solve. The hierarchy problem, the vacuum metastability, the potential for extended Higgs physics, these are the legacies of the discovery, challenges that the next generation of physicists will inherit and perhaps resolve. Gravity and quantum mechanics refuse to speak to each other, and this cosmic standoff has frustrated physicists for a century. You know both theories well by now from their appearances throughout our journey. Gravity, described by Einstein's general relativity, curves space and time around massive objects. Quantum mechanics governs the subatomic world through probability and uncertainty. Both theories are extraordinarily successful in their domains, tested to extraordinary precision, foundations of technologies you use every day. Both theories fail spectacularly when you try to combine them, and the energies at CERN are creeping toward the scales where this failure becomes experimentally relevant, where hints of quantum gravity might finally become visible. General relativity treats spacetime as a smooth, continuous fabric that bends and warps in response to mass and energy. Massive objects like stars and planets create dips in this fabric, and other objects follow curved paths through the warped geometry, what we experience as gravitational attraction. The theory predicts gravitational waves, ripples in space-time produced by accelerating masses, now directly detected by instruments like LIGO. It predicts black holes, regions where space-time curves so severely that nothing can escape, now imaged by telescope arrays spanning the globe. It predicts the expansion of the universe itself, now measured with exquisite precision. But general relativity is fundamentally classical, treating space-time as a definite thing with definite properties, not subject to the fuzziness that quantum mechanics introduces. Quantum mechanics, on the other hand, describes everything as probabilities and waves until measurement forces a definite outcome. Particles don't have exact positions, they have probability distribution spread across space. Energy doesn't come in arbitrary amounts, it comes in discrete quanta, indivisible packets that define the theory's name. The theory is deeply weird by everyday standards. Einstein himself never fully accepted its implications, famously objecting that God does not play dice with the universe. But it works. Every electronic device, every chemical reaction, every biological process operates according to quantum mechanical principles, whether or not our intuitions can encompass them. The problem arises when you try to apply quantum mechanics to gravity itself, treating space-time not as a fixed backdrop, but as a dynamic entity subject to quantum fluctuations. In the quantum world, empty space seethes with virtual particles, fluctuations that briefly borrow energy before returning it. These fluctuations should affect space-time, creating quantum gravitational effects, ripples in the geometry of space at the smallest scales, uncertainty in the very fabric of reality. But when physicists try to calculate these effects using standard techniques that work beautifully for other forces, the mathematics breaks down into infinities that cannot be removed through the usual tricks. The calculations produce nonsense, infinite answers to finite questions, predictions that no measurement could ever match. Historians still argue whether quantum gravity requires a radically new framework, a complete reconceptualization of space, time, and matter, or whether existing approaches will eventually succeed after sufficient mathematical development. String theory proposes that fundamental entities are tiny vibrating strings rather than point particles, and this modification naturally incorporates gravity while avoiding the infinities that plague conventional approaches. Loop quantum gravity attempts to quantize space-time directly, treating space as woven from discrete loops rather than continuous fabric, a network of quantum relationships rather than a smooth manifold. Both approaches have made significant mathematical progress. Neither has produced testable predictions that experiments have confirmed. Here's a quirky detail that captures the challenge. The natural scale for quantum gravity effects is the Planck scale, determined by combining fundamental constants, the speed of light, the gravitational constant, and Planck's constant, into quantities with units of length, time, and mass. The Planck length is about 10 to the negative 35 meters, roughly 100 billion times smaller than a proton, far beyond any conceivable direct measurement. The Planck energy is about 10 to the 19th billion electron volts, roughly a quadrillion times larger than CERN can achieve, requiring an accelerator the size of a galaxy to reach directly. Quantum gravity effects, by this accounting, should be utterly beyond experimental reach, confined to theoretical speculation for the foreseeable future. Yet there are reasons for optimism, glimmers of hope that quantum gravity might reveal itself sooner than this pessimistic estimate suggests. Some theories predict that quantum gravity effects might be enhanced at lower energies through various mechanisms. Extra dimensions could bring the quantum gravity scale down to accessible energies, as we discussed earlier. Modified dispersion relations could cause tiny deviations from standard physics that accumulate over cosmic distances, becoming detectable through astronomical observations. And precision measurements, like those revealing the muon anomaly, might be sensitive to quantum gravitational corrections that more direct searches would miss. The anomalies at CERN probably aren't direct evidence of quantum gravity. The energies involved are still far below the Planck scale by any accounting. But they might be indirect evidence, signs of new physics that connects to quantum gravity in ways theorists haven't fully understood. If supersymmetry explains the anomalies, and supersymmetry is required for string theory's mathematical consistency, then the anomalies would provide evidence for a framework that naturally includes quantum gravity. The connections are indirect and uncertain, but they're real, threads that might eventually weave into a tapestry of unification. You pause before a diagram showing the running of coupling constants, how the strengths of the fundamental forces change with energy scale. At low energies, the energies of everyday life and even of particle physics experiments, the forces have different strengths. Electromagnetism is much weaker than the strong force. The weak force sits somewhere between them. But as energy increases, as you probe smaller and smaller distance scales, the coupling constants converge. In certain theories, including supersymmetric ones, they meet at a single point at very high energies, the grand unification scale, not quite the Planck scale, but approaching it. This convergence might be a hint that the forces unify into a single entity at extreme energies, with gravity joining the unification at even higher scales. The dream of unification has driven physics for over a century, from Maxwell's unification of electricity and magnetism through the electro-weak theory that unified electromagnetism and the weak force. Grand unified theories propose to add the strong force, creating a single framework that encompasses all non-gravitational interactions. The ultimate goal is a theory of everything that incorporates gravity as well, describing all fundamental forces and particles within a single coherent framework. One equation, as physicists sometimes dream, that explains the entire universe. The anomalies at CERN don't achieve this dream. They're far too modest for that. But they might point the way toward it, suggesting that physics beyond the standard model exists, and that this new physics might connect to the deeper structures that unification requires. Every step toward understanding the anomalies is potentially a step toward understanding gravity at the quantum level, toward bridging the century-old divide between general relativity and quantum mechanics. Quantum gravity remains one of the deepest unsolved problems in physics, challenging not just our equations but our concepts. What does it mean for space-time itself to be uncertain, for geometry to fluctuate, for the fabric of reality to be quantum mechanical? The answers, when they come, will transform our understanding of the universe at its most fundamental level, revealing whether space and time are truly fundamental or emergent from something deeper still. Empty space isn't empty, and this might be the strangest fact you'll encounter tonight, stranger even than extra dimensions or the multiverse. The vacuum, what you think of as absolute nothingness, the absence of everything, is actually a roiling sea of quantum activity, particles flickering in and out of existence, fields oscillating with residual energy, uncertainty itself given physical form. And the anomalies at CERN suggest that our understanding of this quantum vacuum might be fundamentally incomplete, that the nothingness we thought we understood contained surprises we haven't yet imagined. Quantum field theory describes empty space not as true emptiness, but as the ground state of all fields, the configuration with the lowest possible energy that's still consistent with quantum mechanics. This ground state isn't static. It fluctuates constantly due to the uncertainty principle. You cannot know both the value of a field and its rate of change with perfect precision, and this limitation forces the vacuum into perpetual activity. virtual particles appear from nothing, exist for fleeting instants permitted by uncertainty, then vanish again before the cosmic accountant catches the discrepancy. The vacuum teems with virtual electrons, virtual photons, virtual quarks, every particle the theory allows, borrowed from the void's energy budget and returned before the debt comes due. These vacuum fluctuations have real, measurable effects that confirm their existence beyond theoretical speculation. The Casimir effect occurs when two metal plates are placed very close together, closer than the wavelengths of most virtual photons. Fewer virtual photons can fit between the plates than outside them, creating a pressure difference that pushes the plates together. This tiny force has been measured in laboratories around the world, confirming that the quantum vacuum is genuinely full of activity even when it appears completely empty. The effect is small, requiring plates separated by micrometers and precision equipment to detect, but it's real, a tangible manifestation of quantum nothingness. The Lamb shift, the small difference between two energy levels in hydrogen that should be identical in classical physics, arises from the electron interacting with vacuum fluctuations. The electron doesn't orbit the nucleus in a clean path. It jitters and wobbles as virtual particles briefly appear nearby, nudging its position and slightly shifting its energy. This shift was one of the early triumphs of quantum electrodynamics, the theory of how light and matter interact, and its precise measurement helped establish QED as the most accurate theory in physics. The muon anomaly you encountered earlier is another example of vacuum effects. The muon's wobble comes partly from its interactions with the virtual particles that fill empty space. Every charged particle drags a cloud of virtual particles around with it, a quantum entourage that affects its properties in measurable ways. The standard model accounts for these contributions with extraordinary precision, summing up millions of quantum interactions to produce predictions that match experiments to 10 decimal places. The fact that the muon wobbles slightly more than predicted suggests that the vacuum contains virtual particles we haven't yet discovered, contributions from new physics that current calculations miss. Historians still argue whether the vacuum should be considered a physical substance or merely a mathematical convenience, whether the virtual particles are real in any meaningful sense or simply bookkeeping devices that help organize calculations. The debate has philosophical dimensions as well as physical ones, touching on questions about what exists and what it means to exist. But whatever the ontological status of virtual particles, their effects are undeniable, measured in countless experiments and essential for understanding how matter and energy behave. Now, here's a quirky detail that might keep you wondering long after tonight. The vacuum state depends on how you're moving. An accelerating observer experiences what's called the Unruh effect. They see empty space filled with thermal radiation, a warm bath of particles that appear real to them, but don't exist for an observer at rest. The vacuum, in this sense, is observer-dependent, a concept that blurs the boundary between existence and non-existence in ways that challenge everyday intuition. What's empty for one observer is full for another, depending only on their state of motion. The anomalies at CERN probe the vacuum in new and unprecedented ways. The muon, wobbling through magnetic fields, samples the vacuum fluctuations through its interactions with virtual particles. If those fluctuations contain contributions from particles beyond the standard model, new virtual entities that we haven't yet discovered, partners to particles we haven't yet produced in collisions, the muon's wobble would deviate from predictions. This is precisely what the measurements show. The vacuum seems to contain something more than we've accounted for, something that tugs on muons in ways our current theories don't predict. One possibility is that the vacuum contains dark sector particles, entities that interact with standard model particles weakly, but contribute to vacuum fluctuations nonetheless. These particles might be too heavy to produce directly in collisions, but light enough to appear virtually, affecting precision measurements while remaining invisible to direct searches. Another possibility involves axions, those hypothetical particles originally proposed to solve problems with a strong force. Axion fields might permeate the vacuum, creating background effects that shift particle properties in subtle ways. A third possibility involves modifications to quantum field theory itself, changes to the fundamental rules governing how vacuum fluctuations work. The vacuum metastability you encountered in the discussion of the Higgs boson connects to these questions in profound ways. The Higgs field has a vacuum expectation value, a non-zero value even in empty space, that gives particles their masses. If this vacuum state is only metastable, the universe might transition to a lower energy state where the Higgs field has a different value. Particle masses would change, chemistry would become impossible, life as we know it would cease to exist. The vacuum isn't just full of fluctuations, it's potentially fragile as well, balanced in a configuration that might not be the universe's final resting state. You find yourself contemplating the floor beneath your feet, the air in your lungs, the space between atoms. All of it contains the quantum vacuum, that strange ground state where nothing and something merge into indistinguishability. The particles that make up your body interact with the vacuum constantly. Their properties shaped by fluctuations you cannot see, but that determine the nature of reality itself. Mass, charge, magnetic moment. All of these emerge partly from vacuum interactions, from the quantum foam that fills what appears to be emptiness. The precision measurements at CERN are essentially probes of the vacuum, instruments for exploring nothingness with unprecedented sensitivity. By measuring particle properties to extreme accuracy, physicists can detect the subtle signatures of vacuum fluctuations and search for deviations from predictions. The anomalies that have emerged are whispers from the vacuum, messages from the quantum void suggesting that we don't yet understand what empty really means. For a few trillionths of a second after the Big Bang, the universe existed in a state so extreme that the ordinary rules of matter didn't apply. Protons and neutrons hadn't formed yet. The quarks and gluons that would eventually compose them swam freely in a super-hot soup called quark-gluon plasma. This is the primordial state from which everything emerged, the mother liquor of all matter, and CERN has recreated it, briefly, fleetingly, in collisions of lead nuclei at nearly the speed of light. What they've found challenges expectations in ways that connect to all the anomalies we've been discussing throughout our journey tonight. Heavy ion collisions at CERN's ALICE detector produce temperatures exceeding 5 trillion degrees, hotter than the centre of any star, hotter than any supernova explosion, hotter than anything in the universe since the first moments after creation. At these temperatures, the strong nuclear force that normally confines quarks inside protons and neutrons becomes too weak to hold them. The quarks break free from their hadronic prisons, swimming alongside gluons in a plasma state that existed when the universe was barely a microsecond old. For an instant shorter than thought, CERN becomes a time machine, recreating conditions that haven't existed naturally for nearly 14 billion years. The properties of this plasma surprised everyone who studied it. Theorists expected it to behave like a gas, quarks and gluons bouncing around independently, interacting weakly because the strong force weakens at high energies, a phenomenon called asymptotic freedom that earned its discoverers the Nobel Prize. The expectation was reasonable. At sufficiently high temperatures, particles should have so much kinetic energy that their interactions become negligible, producing an almost ideal gas of free quarks and gluons. Instead, the quark-gluon plasma behaves like a nearly perfect liquid, flowing with almost zero viscosity, the smoothest fluid ever observed in nature or laboratory. This perfect fluidity suggests that even in the extreme conditions of the early universe, particles interacted more strongly than standard calculations predicted. The plasma doesn't flow like water or even like superfluid helium. It flows with the viscosity approaching the theoretical minimum allowed by quantum mechanics, a limit derived from fundamental principles of uncertainty and thermodynamics. The quarks and gluons in the plasma are somehow maximally correlated, acting collectively rather than independently, despite the enormous energies that should have freed them from mutual influence. Historians still argue whether the perfect fluidity of quark-gluon plasma indicates new physics or unexpected features of quantum chromodynamics, the theory of the strong force that theorists haven't fully understood. The calculations required to predict plasma properties are extraordinarily difficult, involving non-perturbative quantum effects that resist standard mathematical techniques. The strong force is strong, as its name suggests, making approximation methods that work for electromagnetism fail badly for QCD. Lattice calculations, which simulate the strong force on supercomputers by discretizing spacetime into a grid, have made progress but haven't fully explained the observed properties. Here's a quirky detail that illustrates the extreme conditions involved. The quark-gluon plasma at CERN exists for about 10 to the minus 23 seconds, a yoctosecond, roughly the time light takes to cross a proton. In this fleeting instant, the plasma expands, cools, and transitions back into ordinary matter, producing thousands of particles that spray outward into the detector like fireworks frozen in time. Physicists reconstruct the plasma's properties from these debris patterns, working backward from the aftermath to understand the conditions that existed for an unimaginably brief moment. It's forensic science applied to the dawn of time. The connection to the anomalies we've been discussing throughout our journey lies in the behavior of the strong force itself. Quantum chromodynamics is part of the standard model, supposedly well understood after decades of theoretical and experimental work. But the quark-gluon plasma results suggest gaps in our understanding, phenomena that emerge at extreme conditions that laboratory conditions rarely achieve. If the strong force behaves unexpectedly in the hot plasma, it might behave unexpectedly in precision measurements as well, in ways that affect our interpretation of the anomalies. The theoretical predictions for the muon anomaly, for instance, depend heavily on hadronic contributions, effects from virtual quarks and gluons in the vacuum. These contributions are notoriously difficult to calculate because they involve the strong force in regimes where perturbation theory fails. Physicists use various methods to estimate them: phenomenological models based on experimental data, lattice, QCD calculations using supercomputers, dispersive techniques that relate the contributions to measurable quantities. Different methods sometimes produce different answers, leading to debates about which estimate is most reliable. Recent calculations using lattice QCD have produced hadronic contributions that differ from older estimates using other methods. If the lattice results are correct, the discrepancy between the muon anomaly measurement and theory becomes smaller, possibly small enough to eliminate the need for new physics. But other physicists argue that the lattice calculations have their own uncertainties, systematic effects that might not be fully accounted for, and that the discrepancy remains real. The debate is technical and ongoing, involving subtle questions about how to extrapolate lattice results to the continuum limit, how to handle finite size effects, how to estimate uncertainties in quantities that can't be directly measured. You imagine the conditions recreated in the Alice detector, temperatures that existed when the universe was younger than a heartbeat, densities where matter loses its ordinary identity, a return to the primordial state from which stars and planets, and eventually you emerged. The connection between these extreme conditions and the subtle anomalies in muon wobbles or beauty quark decays isn't immediately obvious. but both phenomena probe the same fundamental theory. The strong force governs both the hot plasma and the hadronic vacuum contributions, and understanding one might illuminate the other. The quark-gluon plasma also provides insights into the early universe's evolution, insights that connect particle physics to cosmology. The transition from plasma to ordinary matter, called hadronization, seeded the protons and neutrons that eventually formed atoms during the epoch of recombination, gathered into galaxies under gravitational attraction, fused into heavier elements in stellar cores, and eventually constructed the planet you inhabit and the body you wear. Understanding this transition means understanding how the universe became what it is today, tracing the causal chain from the first microsecond to the present moment. Any surprises in plasma behavior could propagate forward to affect cosmological history. If the strong force has properties we haven't fully understood, the hadronization process might have proceeded differently than standard models assume, producing slightly different abundances of protons and neutrons, slightly different conditions for nucleosynthesis, slightly different patterns in the cosmic microwave background. The precision of cosmological observations constrains these possibilities, but the constraints aren't absolute. Room exists for surprises that connect particle physics to the larger scales. Why does anything weigh anything? The question sounds almost childish until you realize that physics doesn't have a complete answer. The Higgs mechanism explains how particles acquire mass through their interactions with the Higgs field, but it doesn't explain why those interactions have the strengths they have. The masses of fundamental particles seem arbitrary, disconnected from any deeper principle, their values determined by experiment rather than prediction. And the anomalies at CERN suggest that even this incomplete understanding might be missing crucial pieces, that mass itself harbours mysteries we've only begun to appreciate. Consider the pattern of particle masses, if pattern is even the right word for such apparent chaos. The electron weighs about 0.005 of a proton, a tiny mass, yet essential for the chemistry that makes life possible. The muon weighs about 1/10 of a proton, roughly 200 times heavier than the electron it resembles in every other way. The tau lepton weighs almost twice as much as a proton, a heavyweight among leptons, decaying so quickly that it barely travels a millimeter before transforming into lighter particles. Why these ratios? Why is the muon exactly this much heavier than the electron, neither more nor less? The standard model provides no answer. It simply accepts the masses as inputs, measured values that must be fed into the theory rather than derived from it. The same mystery applies to quark masses, which span an even more dramatic range. The up and down quarks that compose protons and neutrons have masses of only a few million electron volts, negligible compared to the proton's mass, which comes mostly from the energy of the strong force binding the quarks together. The strange quark weighs roughly 100 million electron volts. The charm quark tips the scales at over 1 billion electron volts. The bottom quark is heavier still, and the top quark, discovered at Fermilab in 1995 after decades of searching, weighs over 170 billion electron volts, roughly as heavy as an entire gold atom, the most massive fundamental particle known. This enormous hierarchy of masses cries out for explanation, but none is forthcoming from current theories. The Higgs mechanism works by giving particles mass proportional to their coupling to the Higgs field, their interaction strength with the omnipresent background that permeates all of space. But what determines these couplings? Why does the top quark couple so strongly while the electron couples so weakly? Some physicists believe the answer lies in deeper structures, additional symmetries, extra dimensions, compositeness, that constrain the couplings and predict the masses. Others worry that the masses might be environmental, determined by our particular universe but varying in others, making prediction impossible and explanation unnecessary. historians still argue whether the mass hierarchy problem is a genuine puzzle, requiring new physics, or simply the way nature happens to be, an accident of cosmic history rather than a reflection of deeper law. The anthropic principle offers a partial explanation. If particle masses were very different, atoms wouldn't form in the ways necessary for chemistry, stars wouldn't burn in the ways necessary for energy, life wouldn't exist to ask questions about masses. We necessarily observe masses compatible with our existence, regardless of whether those masses have deeper explanations. But this explanation feels unsatisfying to many physicists, substituting selection for mechanism, accepting arbitrariness rather than explaining it. Here's a quirky detail that highlights the mystery. The masses of the 3 generations of quarks and leptons seem to follow roughly geometric progressions, each generation heavier than the last by factors that might not be coincidental. The electron, muon and tau have masses in ratios of roughly 1 to 200 to 3500, spanning nearly 4 orders of magnitude in a pattern that might reflect underlying structure. Some theorists have searched for mathematical formulas relating the masses, hoping to find patterns that reveal hidden organization. Tantalizing hints have emerged, relationships that almost work, formulas that nearly predict, but no convincing explanation has gained broad acceptance. The anomalies at CERN touch on the mass mystery in unexpected ways that make the puzzle more acute. The muon wobble and beauty quark decays both involve heavier particles behaving differently from their lighter cousins. If new physics couples preferentially to heavier leptons, as the anomaly suggests, this preferential coupling might connect to whatever mechanism determines the mass hierarchy in the first place. The masses and the anomalies might both emerge from the same underlying structure, different manifestations of physics we haven't yet discovered. One particularly intriguing possibility involves the concept of flavor, which in physics refers not to taste but to the different types of quarks and leptons. There are 3 flavors of charged leptons, electron, muon, tau, and 6 flavors of quarks, up, down, charm, strange, top, bottom. The standard model treats flavor as basically arbitrary. The different flavors exist, they have different masses, they can transform into each other through weak interactions, and that's all there is to say. Flavor is a label, not explanation, a way of distinguishing particles without understanding why the distinctions exist. But the anomalies suggest that flavor might be more structured than this superficial treatment implies. The violation of lepton universality, the different treatment of electrons and muons in beauty quark decays, indicates that nature distinguishes between flavors in ways beyond mere mass difference. New symmetries or new particles might organize the flavors into patterns we haven't yet recognized, explaining both the mass hierarchy and the anomalous behavior simultaneously. Flavor physics has become a hot topic precisely because of the LHC-B anomalies, with theorists proposing new frameworks and experimentalists designing new measurements to test them. You contemplate the masses of the particles that compose you, the up and down quarks inside your protons and neutrons, the electrons orbiting your nuclei in clouds of probability. These masses determine the properties of atoms, the strengths of chemical bonds, the size of biological molecules. A slight change in mass values would produce a universe unrecognizable from our own, possibly hostile to any form of organized complexity. The universe appears fine-tuned for existence, and the masses are part of that tuning, parameters that must fall within narrow ranges for stars to shine and planets to form and life to emerge. Whether this fine-tuning reflects deep structure, environmental selection, or something else entirely remains unknown, one of the great open questions of fundamental physics. The anomalies at CERN offer the possibility of progress, hints that new physics related to flavor and mass might be within experimental reach. For the first time in decades, the mass hierarchy problem might be transitioning from philosophical puzzle to empirical science, from something we wonder about to something we might actually solve. Time flows forward, never backward, and this obvious fact about the universe conceals one of physics' deepest mysteries. The fundamental laws governing particles, the equations of the Standard Model, work almost perfectly the same whether time runs forward or backward. Yet the universe clearly distinguishes past from future. Eggs break but don't unbreak. People age but don't grow younger. Entropy increases but never spontaneously decreases. This arrow of time emerges from somewhere, and CERN's anomalies might be revealing where, pointing toward asymmetries in fundamental physics that could explain why time has a direction at all. At the particle level, most processes are time-symmetric in a way that seems to mock our everyday experience. A collision that produces certain particles could run backward in time, with those particles recombining to form the original collision products, and the laws of physics would be equally satisfied. Film a billiard break and play it backward. Aside from the improbability of all the balls converging perfectly, no law of physics would be violated. The mathematics doesn't care which direction time flows. The equations remain valid either way. This time reversal symmetry seems to be built into the fundamental structure of physical law, but time reversal symmetry combines with other symmetries in ways that physics has carefully studied. Charge conjugation symmetry, called C, exchanges particles with antiparticles. Parity symmetry, called P, reflects space through a mirror, exchanging left with right. Time reversal symmetry, called T, reverses the flow of time. Together, these three symmetries combine into CPT symmetry, and CPT symmetry is believed to be absolutely exact in nature, a fundamental property of quantum field theory that cannot be violated without destroying the mathematical consistency of physics itself. The exactness of CPT symmetry means that if one of the component symmetries is violated, the others must compensate. CP violation, where processes differ between particles and antiparticles even after spatial reflection, has been observed in the decays of neutral kaons and B mesons, small but measurable differences that earn their discoverers the Nobel Prize. T violation, where processes genuinely differ when time is reversed, has also been observed, linked to CP violation through CPT conservation. These violations are small, involving rare processes and subtle asymmetries, but they're real, experimentally confirmed departures from perfect symmetry. Historians still argue whether the observed CP and T violations are sufficient to explain the arrow of time, or whether additional mechanisms must exist beyond what current physics provides. The Standard Model's CP violation is far too weak to explain the baryon asymmetry of the universe, that puzzle you encountered earlier about why matter survived the antimatter annihilation. If new physics introduces additional sources of CP violation, it might simultaneously explain the matter-antimatter asymmetry and contribute to our understanding of time's direction, connecting microscopic asymmetries to macroscopic irreversibility. Here's a quirky detail that makes the mystery concrete. Neutral kaons, particles containing a strange quark paired with an anti-down quark, oscillate between particle and antiparticle states, transforming back and forth through quantum mechanical mixing. These oscillations violate CP symmetry slightly, proceeding at different rates depending on whether you're going from particle to antiparticle or the reverse. The effect was first observed in 1964 at Brookhaven National Laboratory and remains one of the most precise confirmations of CP violation in nature. Similar effects occur in neutral mesons, particles containing beauty quarks, which CERN studies intensively at the LHCb detector. The anomalies in beauty quark decays connect directly to this physics of symmetry violation. The violation of lepton universality, electrons and muons being treated differently might indicate new sources of CP violation beyond those the standard model provides. If the new physics responsible for the anomalies also introduces additional CP violating phases, this could have profound implications for cosmology and for our understanding of time's direction. The same physics that makes muons behave unexpectedly might explain why the universe contains matter rather than nothing. Some physicists speculate that time itself might emerge from deeper structures rather than being fundamental, an illusion created by thermodynamics rather than a basic feature of reality. In certain approaches to quantum gravity, time doesn't exist at the most fundamental level. It emerges from quantum entanglement and thermodynamic processes, a collective phenomenon arising from underlying timeless physics. If this view is correct, the arrow of time might not require explanation through particle physics at all. It might be a consequence of how the universe organizes information at macroscopic scales, independent of microscopic symmetries. You notice the clocks on the wall of the control room in your imagination, their hands moving steadily forward, marking time in the ordinary way that clocks do. But down here in the tunnels of CERN, in the collisions of particles travelling near the speed of light, time behaves strangely. Muons live longer than they should because time dilation stretches their lifespans. Special relativity in action, demonstrated millions of times per day in these underground chambers. Particle decays that would be instantaneous at rest take measurable time in the laboratory frame, because the decaying particles are moving so fast that their internal clocks run slow. The asymmetry between past and future might ultimately connect to the initial conditions of the universe, the low entropy state of the Big Bang, from which entropy has been increasing ever since like water flowing downhill. But why the Big Bang had low entropy remains unexplained, a boundary condition imposed on the equations rather than derived from them. The anomalies at CERN don't directly address this cosmological question, but they contribute to the larger picture of symmetry and its violations that shapes our understanding of time's arrow. Every collision in the Large Hadron Collider is a tiny experiment in time symmetry, a probe of how fundamental physics treats the direction of time. Particles produced in collisions decay, according to laws that are almost but not perfectly symmetric under time reversal. By measuring these decays with extreme precision, physicists can search for new violations, new asymmetries, new clues to the origin of time's arrow. The hunt continues, driven by anomalies that suggest our current theories are incomplete, that somewhere in the data lies evidence of new physics that distinguishes past from future more strongly than the standard model allows. Perhaps our universe is just one bubble in an infinite foam of realities, each with different laws, different constants, different possibilities. The multiverse hypothesis has lurked at the edges of physics for decades, dismissed by some as unscientific speculation, embraced by others as the inevitable conclusion of our best theories. And if CERN's anomalies truly indicate that the standard model is breaking down, the multiverse might offer the only framework capable of explaining why our universe has the specific properties it does, including properties that seem inexplicably fine-tuned for the emergence of complexity in life. The multiverse enters physics through several doors, each one leading from respectable theoretical physics into territory that makes some scientists deeply uncomfortable. In eternal inflation, the rapid expansion of the early universe, the inflationary epoch that smoothed out primordial wrinkles and set the stage for the Big Bang we observe, continues forever in some regions while ending in others, creating an infinite number of pocket universes that expand away from each other, never to interact again. Each pocket universe might have different physical properties, different values of fundamental constants, different particles and forces, a cosmic lottery played out across infinite variations. In string theory's landscape, the vast number of possible vacuum states, estimated at 10 to the 500th power or more, a number so large it defies comprehension, might all be realized in different regions of a multiverse. Each vacuum state corresponds to a different possible configuration of the extra dimensions that string theory requires, and each configuration produces different low-energy physics, different particles, different laws. Our universe, with its specific standard model and its specific anomalies, would be just one possibility among unimaginably many. In the many worlds interpretation of quantum mechanics, every quantum measurement splits reality into branches where all possible outcomes occur, with observers in each branch experiencing only their particular result. This interpretation, proposed by Hugh Everett in 1957, and long considered a fringe idea, has gained respectability in recent decades, as physicists have struggled to make sense of quantum mechanics without the measurement problem that other interpretations face. What connects these speculative frameworks to the anomalies at CERN is the question of naturalness, the expectation that physical parameters should take values that seem typical rather than special. The standard model, as we've discussed throughout our journey, contains parameters that seem fine-tuned. The Higgs mass balanced against enormous quantum corrections, the cosmological constant inexplicably tiny, the masses of particles following patterns that suggest hidden order without revealing what that order might be. In a single universe, this fine-tuning demands explanation, crying out for new physics that would make the parameters natural. In a multiverse, it becomes selection. We necessarily find ourselves in a universe compatible with our existence, regardless of how rare such universes might be among all possibilities. Historians still argue whether the multiverse represents genuine physics or a retreat from explanation, whether it's a scientific theory that makes predictions or a philosophical position that explains everything by explaining nothing. Critics call it unfalsifiable. If other universes are causally disconnected from ours, we can never observe them directly, making multiverse claims immune to experimental test. The multiverse might be true, but we could never know it's true, which arguably places it outside the domain of science. Defenders respond that indirect evidence might exist, signatures in the cosmic microwave background radiation, correlations in fundamental constants, patterns in particle physics that make sense only in a multiverse context. Here's a quirky detail that illustrates the debate. Nobel laureate Steven Weinberg used multiverse reasoning to predict the approximate value of the cosmological constant, the energy density of empty space that drives the universe's accelerating expansion, before it was measured, arguing that much larger values would prevent galaxy formation and thus observers to measure them. The universe's cosmological constant had to be small enough for galaxies to form, and Weinberg estimated how small based on this anthropic constraint. When the cosmological constant was measured a few years later, it was roughly in the range Weinberg had predicted. The successful prediction impressed some physicists while leaving others unconvinced, demonstrating how controversial multiverse reasoning remains. The anomalies at CERN might either support or undermine multiverse thinking, depending on how they are eventually explained. If new particles are discovered that explain the muon wobble and beauty quark decays, these particles would reduce the apparent fine-tuning of the standard model, making multiverse reasoning less necessary. Why invoke an infinity of other universes when our universe can be explained with a few additional particles? But if the anomalies persist without simple explanations, if the new physics itself requires fine-tuning, the multiverse might become more attractive as a framework for understanding why our universe has the properties it does. Some versions of the multiverse predict that physical constants vary across different regions of cosmic space, changing gradually over distances far larger than the observable universe. If this were true, subtle variations in constants might be observable through astronomical measurements of distant objects whose light has travelled for billions of years from regions that might have slightly different physics. So far, no such variations have been convincingly detected. The fine structure constant, the gravitational constant, and other fundamental parameters appear uniform throughout the observable universe within measurement precision. But the searches continue, motivated partly by theoretical frameworks that suggest variation should occur. You find yourself imagining the unimaginable, an infinity of other universes, some similar to ours, most radically different, each real in its own right, each populated, or not, by its own observers asking their own questions about their own anomalies. In some universes, the standard model might work perfectly, with no hints of new physics. In others, the anomalies might be enormous, impossible to miss. In still others, physics might be so different that concepts like particles and forces don't even apply. The thought produces a strange mixture of humility and vertigo, a reminder that our corner of existence might be infinitesimally small compared to what exists. The philosophical implications of the multiverse extend beyond physics into questions about meaning, uniqueness, and existence. If infinite versions of you exist across the multiverse, making every possible choice, living every possible life, does individual choice matter? If our universe is just one among countless others, is it special in any meaningful sense? Or is its apparent specialness an illusion created by our limited perspective? These questions have no scientific answers, but they emerge naturally from contemplating the possibilities that theoretical physics has opened. The physics community isn't presenting a united front, and that's exactly how science should work. Walk through any department meeting, conference dinner, or online forum where physicists gather, and you'll find passionate disagreement about what CERN's anomalies mean, whether they're real, and what to do about them. This ferment of debate might look like confusion from outside, might seem to undermine the authority of scientific consensus. But it's actually the scientific method in action. Ideas competing, arguments clashing, evidence being weighed and reweighed until something approaching truth emerges from the noise. On one side stand the enthusiasts, physicists who believe the anomalies herald a new era of discovery that will transform our understanding of nature. They point to the pattern of deviations all pointing in similar directions, the persistence of signals across different experiments and analysis methods, the theoretical motivations for physics beyond the standard model that have accumulated over decades. For them, the anomalies are Christmas morning after a long winter of null results, wrapped packages that might contain the long-awaited breakthrough beyond 50 years of standard model dominance. Some have already started writing papers about what the new physics might be, constructing models, making predictions, staking their reputations on the reality of signals that others dismiss. On the other side stand the skeptics, equally accomplished physicists who have seen anomalies come and go before, who have learned through hard experience not to trust early results, no matter how exciting they seem. They remember the superluminal neutrinos of 2011, a result from CERN's Opera experiment that seemed to show neutrinos travelling faster than light. Impossible, according to relativity, revolutionary if true. The physics community went wild with speculation for months until investigators discovered that a loose fibre optic cable had introduced timing errors. They remember the diphoton excess of 2015, a statistical bump in the data that thousands of theorists interpreted as a new particle, spawning hundreds of papers before the excess evaporated with more data. Historians still argue whether skepticism or enthusiasm has better served physics over the long run, whether science advances more through bold leaps or through cautious consolidation. Healthy skepticism prevents wild goose chases and keeps standards high, ensuring that claimed discoveries are real before the community invests resources in pursuing them. But excessive skepticism might dismiss genuine discoveries, delaying progress while demanding impossibly high burdens of proof, waiting for certainty that nature never provides. The balance between openness and rigour is delicate, and different physicists strike it differently based on their personalities, their experiences, and their positions in the field. Here's a quirky detail that captures the sociology of the field. When collaboration members vote on whether to publish an anomaly, the votes often split along generational lines. Senior physicists who've lived through previous disappointments tend toward caution, remembering how many times they've been burned by results that seemed solid. Junior physicists, whose careers might be made by a major discovery and who haven't yet been scarred by false alarms, push for aggressive interpretation, eager to stake their claims before competitors do. The published papers often represent compromises, hedging language masking genuine disagreement about what the results mean, caveats and qualifications that allow multiple interpretations. The theoretical community has responded to the anomalies with an explosion of creativity. Hundreds of papers proposing explanations, each one constructing models that could account for the observed deviations while remaining consistent with other measurements. Leptoquarks, particles that would connect quarks and leptons in ways the standard model doesn't allow. Z-prime bosons, heavy cousins of the Z boson that might mediate new forces. Extended gauge symmetries that add new force-carrying particles to the mix. Loop effects from new particles that are too heavy to produce directly, but influence precision measurements through virtual contributions. The menu of possibilities has expanded enormously, limited only by theorists' imagination and the constraints of mathematical consistency. But theorists are also divided. Some build models optimistically, assuming the anomalies are real and new physics awaits, positioning themselves to say, "I predicted that," when discoveries are announced. Others focus on standard model uncertainties, arguing that better calculations might make the anomalies disappear, that the discrepancies reflect our limited understanding of hadronic physics or statistical fluctuations rather than genuine new phenomena. The optimists accuse the pessimists of lacking imagination. The pessimists accuse the optimists of wishful thinking. Both sides can point to historical precedents supporting their positions. The experimental community faces its own challenges that are fundamentally different from theoretical disputes. The anomalies are subtle enough that they require enormous datasets and exquisite control over systematic uncertainties. Different experiments sometimes produce slightly different results, leading to debates about whose analysis is more reliable, whose detector is better understood, whose systematic error estimates are more credible. Blind analysis techniques, where physicists don't know what the data says until the analysis methods are finalized, help prevent bias, ensuring that the analysis choices aren't influenced by knowledge of where they'll lead. But blind analysis can't eliminate all sources of disagreement, all differences in methodology and interpretation. You imagine the conversations happening in offices and hallways throughout CERN, the arguments over coffee in the cafeteria, the late-night emails between collaborators on different continents who've never met in person, but share responsibility for results that might reshape physics. Physics is a human endeavour, conducted by people with hopes and fears, careers and reputations, egos and insecurities. The image of the dispassionate scientist, rationally evaluating evidence without emotional investment, is a fiction, perhaps a useful fiction, that provides an ideal to aspire to, but a fiction nonetheless. Real scientists care deeply about their work, and that caring produces both breakthroughs and blind spots. The disagreements ultimately will be resolved by data, by nature's testimony that cannot be argued with or wished away. More muon measurements will either strengthen or weaken the anomaly. More beauty quark decays will either confirm or contradict the hints of lepton universality violation. Upgraded detectors will provide higher precision. New experiments will cross-check results from different angles, using different techniques, subject to different systematic uncertainties. Eventually, the truth will emerge, not because physicists agreed in advance, but because nature has the final vote, and nature cannot be lobbied or persuaded. This process of disagreement and resolution is science's greatest strength, the feature that distinguishes it from other ways of knowing. Unlike religious or political debates, where fundamental axioms prevent resolution, scientific debates have a referee that cannot be argued with. The evidence speaks, and eventually the community listens. Some physicists will be vindicated, others will need to revise their views. The humiliation of being wrong is balanced by the joy of being right, and both experiences drive the enterprise forward. The Large Hadron Collider is already a monument to human ambition, but it won't remain the world's most powerful accelerator forever. Plans are underway for even larger machines, designed to either confirm or bury the anomalies we've been discussing, to push beyond the current frontier into territory where new physics might finally reveal itself unambiguously. The future circular collider, proposed to be built in the same region as CERN, would dwarf its predecessor with a circumference of 100 kilometers, more than twice the length of a marathon, and collision energies 7 times higher than the LHC achieves today. If built, the future circular collider would probe distances even smaller than those accessible today, searching for new particles and forces that current experiments can only hint at through precision measurements. The direct production of heavy particles, leptoquarks, Z-prime bosons, supersymmetric partners, whatever might be responsible for the anomalies, would become possible at masses far beyond the LHC's reach. Instead of inferring new physics from its subtle effects on muon wobbles or quark decays, physicists could potentially create new particles directly, studying their properties with the same detail they've applied to the Higgs boson and top quark. The motivations for such a machine extend beyond the current anomalies, important as they are. Even if the muon wobble and beauty quark deviations evaporate with better measurements, the questions they highlight, the hierarchy problem, dark matter, the origin of particle masses, remain unanswered. A more powerful collider could produce particles too heavy for current machines, directly creating whatever new physics lies beyond the standard model, rather than inferring it from subtle effects in precision measurements. The exploration of the energy frontier is a scientific imperative, regardless of whether current hints pan out. The future circular collider isn't the only proposal competing for resources and attention. China has discussed building its own circular collider, the CEPC, potentially followed by a proton-proton machine similar to the FCC. The project would represent China's emergence as a leader in fundamental physics, a statement of scientific ambition on par with the space programs of the 20th century. Linear colliders using new acceleration technologies might achieve high energies and smaller footprints, trading the repetitive circulation of a ring for the straight-shot acceleration of a single pass. Muon colliders, which accelerate muons instead of protons, could probe energies comparable to the FCC in machines 1/10 the size, though the technical challenges of handling unstable particles that decay in microseconds remain formidable. Historians still argue whether big colliders represent the best investment for particle physics, or whether smaller, more targeted experiments might produce better returns. The cost of the FCC is estimated at over $20 billion, comparable to the budget of a major space program, requiring contributions from multiple nations over decades of construction and operation. Critics argue this money could fund thousands of smaller experiments, exploring multiple avenues simultaneously rather than betting everything on one machine. What if the new physics isn't at higher energies? What if the anomalies are explained by light particles that escape detection rather than heavy ones beyond reach? Here's a quirky detail about the engineering challenges. The FCC would require magnets more than twice as powerful as those in the current LHC, pushing superconducting technology to its limits and perhaps beyond what's currently achievable. The machine would consume as much electricity as a small city and require cooling systems capable of maintaining temperatures near absolute zero across a tunnel longer than the distance from Midtown to downtown Manhattan. Building it would be one of the largest engineering projects in human history, comparable to the construction of the pyramids or the Apollo program, but aimed at understanding reality rather than reaching the moon. Beyond Earth-based colliders, space-based experiments offer complementary approaches that don't require the massive infrastructure of terrestrial accelerators. The Alpha Magnetic Spectrometer on the International Space Station has been searching for dark matter signals in cosmic rays since 2011, looking for anomalies in the composition of particles raining down from space that might indicate dark matter annihilation or decay. Proposed missions would study antimatter, measure gravitational waves, or search for variations in fundamental constants across cosmic distances. These experiments can't achieve the energy densities of colliders, but they can accumulate data over years of operation, sampling cosmic particles that nature accelerates for free in supernova shockwaves and other astrophysical engines. Underground laboratories, shielded from cosmic rays by kilometers of rock, host experiments searching for rare processes, proton decay, dark matter interactions, neutrinoless double beta decay. These ultra-rare events, if observed, would provide evidence for physics beyond the standard model that colliders might miss. Proton decay, predicted by grand unified theories but never observed, would confirm that the forces unify at high energies even if we can't directly access those energies in accelerators. Neutrinoless double beta decay would prove that neutrinos are their own antiparticles, with profound implications for the matter-antimatter asymmetry of the universe. You imagine physicists decades from now, working with machines we can barely conceive, asking questions we haven't yet thought to ask. The history of physics has been a story of expanding horizons, new energies revealing new particles, new scales revealing new laws, new technologies enabling new discoveries. The anomalies at CERN represent the current frontier, but frontiers are made to be pushed outward. Every generation of physicists has discovered something the previous generation couldn't have imagined, and there's no reason to think our generation will be the last. The decisions about which experiments to build will be made by committees, funding agencies and governments, balancing scientific priorities against competing demands for resources. These decisions involve uncertainty. No one can guarantee that a particular machine will make the discoveries hoped for. Superconducting Super Collider, cancelled in 1993 after billions of dollars spent, stands as a reminder that big physics projects can fail politically even when they're scientifically sound. But the decisions also involve opportunity. The chance to be present at the moment when new physics is revealed, when the standard model's cracks open into windows onto deeper reality. Whether the next breakthrough comes from a giant circular collider, a compact muon machine, an underground detector, or a satellite in orbit, it will emerge from the same process that has driven physics forward for centuries: curiosity, ingenuity, collaboration, and the stubborn conviction that nature's secrets can be uncovered by persistent inquiry. What if the crack in physics cracks everything else? The implications of rewriting fundamental physics extend far beyond academic journals and conference presentations, far beyond the debates among specialists that occupy the corridors of CERN. Technologies, philosophies, and our understanding of what it means to exist, all of these might shift if the anomalies at CERN reveal genuinely new physics, rippling outward from particle physics laboratories into the broader human world in ways we can barely anticipate. Start with technology. The standard model wasn't developed with practical applications in mind. Physicists pursuing the anomalies that led to quarks and gluons and the Higgs boson weren't thinking about consumer products or industrial processes, but the technologies spawned by fundamental physics are everywhere, so woven into daily life that we forget their origins. The World Wide Web was invented at CERN to help physicists share data from the LEP collider, a communication tool that transformed human civilization within a single generation. PET scanners, which detect antimatter produced inside your body during certain metabolic processes, emerge from particle physics research into positron detection. The understanding of semiconductors that underlies every computer and smartphone rests on quantum mechanics, the very framework that might need revision if the anomalies indicate new physics. If new physics exists, new applications will eventually follow, though predicting them in advance is impossible. That's the nature of fundamental research, that its applications are unforeseeable, precisely because the discoveries themselves are unforeseeable. Who could have predicted when Einstein wrote about the photoelectric effect that his explanation would lead to solar cells and digital cameras? Who could have predicted when quantum mechanics was being formulated that it would enable the transistors that power the information age? The anomalies at CERN might point toward physics that eventually enables technologies as transformative as those earlier discoveries, or they might remain forever academic, scientifically fascinating but practically inert. Quantum computing represents one area where fundamental physics directly enables technology, where the strange properties of quantum mechanics become computational resources. Current quantum computers manipulate quantum states according to standard model physics, exploiting superposition and entanglement to perform calculations impossible for classical computers. If that physics is incomplete, new phenomena might be exploitable, new types of quantum states, new ways of processing information, new computational capabilities. This is highly speculative, of course, but the history of physics suggests that deeper understanding eventually yields deeper tools, that the arc of knowledge bends toward application even when the path is invisible. Historians still argue whether fundamental research justifies its expense through technological spin-offs, or whether it should be valued for its own sake, whether the practical benefits are happy accidents or essential justifications. The debate has practical consequences. Funding agencies allocate billions of dollars based on expectations of return, and physicists must continually justify their work to skeptical policymakers who prefer investments with clearer payoffs. The anomalies at CERN don't directly promise new technologies. No one is claiming that muon wobbles will lead to better smartphones, but they do promise deeper understanding from which technologies have historically emerged. Here's a quirky detail that connects abstract physics to everyday life. GPS satellites must account for both special and general relativistic effects to provide accurate positioning. Time passes slightly differently on orbiting satellites than on Earth's surface, faster due to their distance from Earth's gravity, slower due to their orbital velocity, and without corrections based on Einstein's theories, GPS would drift by kilometers per day, rendering it useless. The physicists who developed relativity couldn't have imagined GPS, yet their abstract theories about space and time now guide billions of people every day. Future applications of whatever new physics emerges from CERN's anomalies might be equally surprising. Beyond technology, the philosophical implications of new physics deserve consideration, though they are necessarily more speculative. The Standard Model, despite its incompleteness, has supported a broadly materialist worldview. The idea that everything can ultimately be explained in terms of particles and forces, that the universe is fundamentally mechanical, even if the mechanics are quantum. If new physics introduces genuinely new concepts, extra dimensions, parallel universes, fundamental limits on knowledge, these might require philosophical adaptation, new ways of thinking about reality that we haven't yet developed. The relationship between consciousness and physics remains mysterious, one of the hard problems that neither physics nor philosophy has solved. Some physicists speculate that quantum mechanics plays a role in brain function, that the collapse of wave functions or quantum entanglement contributes to mental processes in ways that classical physics couldn't accommodate. This remains deeply controversial, dismissed by many neuroscientists as mysticism, but it hasn't been definitively refuted. If new physics involves new quantum phenomena, it might shed light on the mind-body problem, or it might simply add new layers of complexity to an already difficult question. You contemplate the cascade of consequences that might flow from a few anomalous decimal places in particle physics measurements. The muon wobbles a bit too much. Therefore our understanding of the vacuum is incomplete. Therefore new particles exist. Therefore the universe contains more stuff than we knew. Therefore our picture of reality requires revision. Each step is uncertain, conditional, subject to future evidence that might confirm or contradict it. But the chain exists, linking abstract measurements in underground laboratories to concrete implications for how we understand ourselves and our place in the cosmos. The anomalies at CERN won't be resolved quickly. This is one prediction we can make with confidence. Years of additional data collection, analysis and debate lie ahead. Careers will be built and ended, theories proposed and abandoned, experiments designed and executed. The process will be messy, contentious, and ultimately productive. Science advances not by smooth progress, but by cycles of crisis and resolution, anomaly and explanation, confusion and clarity. For now, the anomalies represent questions rather than answers. They point toward possibilities without confirming them. They challenge the standard model without replacing it. They invite speculation without rewarding certainty. This liminal state, between the known and the unknown, the established and the revolutionary, is uncomfortable, but also fertile. Great discoveries emerge from such states, when old frameworks strain and new ones gestate, when the tension between data and theory becomes impossible to ignore. The implications of new physics will unfold gradually, over decades rather than years. But they will unfold, as physics has always unfolded, transforming technology, revising philosophy, reshaping the human understanding of what the universe is and what we are within it. And so you arrive at the strangest comfort of all, not knowing. The anomalies at CERN don't provide answers, they provide questions. The cracks in the standard model don't reveal what lies beyond, they merely suggest that something does. You came here tonight expecting perhaps a revelation, a solution, a tidy conclusion to the mysteries of the universe wrapped up with a bow and delivered to your doorstep. Instead, you find something better, an invitation to wonder, an opening rather than a closure, a beginning disguised as an ending. The beauty of uncertainty lies in what it implies about the adventure ahead. If we knew everything, there would be nothing left to discover, no frontiers to explore, no surprises awaiting in the data. The anomalies at CERN represent the opposite of completion. They represent opening, expansion, the ongoing adventure of understanding that has driven humanity since someone first looked up at the stars and asked what they were. Every physicist who stays late analysing data, every theorist who builds models on whiteboards covered with equations, every student who reads papers hoping to contribute something new, all of them participate in something larger than any individual career, a multi-generational project to comprehend reality that has no defined endpoint. Consider what humanity has accomplished in just a few centuries of systematic scientific inquiry, a blink of an eye in evolutionary terms. We discovered atoms, then discovered that atoms have structure, nuclei surrounded by electrons in quantum probability clouds. We discovered that nuclei have structure too, protons and neutrons bound by the strong force. We discovered that protons and neutrons have structure still deeper, quarks held together by gluons, the strong forces carriers. At every level, what seemed fundamental turned out to be composite. What seemed final turned out to be provisional. The anomalies at CERN suggest this pattern continues, that the quarks and leptons and force carriers of the standard model might themselves be manifestations of something deeper still. We invented mathematics to describe motion, then realized motion warps time in ways that mathematics had to stretch to accommodate. We built machines capable of accelerating particles to speeds where time dilation becomes measurable, where the bizarre predictions of relativity become everyday laboratory facts. We uncovered forces invisible to the senses: electromagnetism, the weak force, the strong force, and learned to manipulate them for technologies our ancestors would have called magic. This trajectory shows no signs of ending. The anomalies suggest it's accelerating, that we stand at the threshold of discoveries as profound as any in physics history. Historians still argue whether scientific progress is inevitable or contingent, whether the discoveries would have happened eventually regardless of who made them, or whether different choices, different personalities, different funding decisions might have led to entirely different understandings. What seems certain is that humanity possesses an apparently endless capacity for curiosity, a drive to ask why and how that no amount of discouragement extinguishes. Children ask why the sky is blue before they can tie their shoes. Physicists ask why muons wobble after decades of training. The impulse is the same, a refusal to accept mystery as final, a conviction that understanding is possible even when it seems impossibly remote. Here's a quirky detail that might bring a smile as we near the end of our journey. Many of the physicists working on CERN's anomalies were inspired by science fiction they read as children, stories of distant galaxies and strange forces that turned out to be less fanciful than reality itself. The universe, it seems, outpaces imagination. The actual physics of quantum mechanics and relativity is stranger than any fiction ever conceived, filled with particles that exist in multiple places at once, dimensions that might curl up too small to see, vacuums that seethe with energy and threaten to decay into different vacuums that would remake the cosmos. The anomalies might add new chapters to this strangeness, phenomena that today's science fiction hasn't yet imagined, but that tomorrow's children will read about with wonder. You think back over the journey you've taken tonight, the muons wobbling too much, the beauty quarks decaying unexpectedly, the neutrinos appearing in surplus, the antimatter that should have destroyed everything, the dark matter holding galaxies together, the supersymmetric partners that never showed up, the extra dimensions that might hide reality's true shape, the Higgs field balancing on a knife's edge, the quantum vacuum seething with possibility, the quark-gluon plasma recreating the dawn of time. Each mystery connects to the others, threads in a tapestry that we can only partially perceive, patterns emerging from what seems like chaos. The future is uncertain. We've said that many times tonight, and it bears repeating one more time. The anomalies might evaporate with better measurements, joining the superluminal neutrinos and diphoton excesses in the dustbin of statistical fluctuations. Or they might strengthen, crossing the thresholds of statistical significance that would force even the skeptics to admit that new physics has been found. Either outcome advances our understanding. Either outcome is a victory for science. The method works regardless of where it leads, producing knowledge that accumulates across generations, building a picture of reality that becomes clearer with each discovery. And now your eyelids grow heavy, the weight of the universe settling gently upon them like a blanket woven from starlight and mystery. The hum of CERN's machinery fades into the distance, replaced by the soft rhythm of your own breathing, the quiet pulse of your own heart carrying atoms forged in ancient stars. The questions we've explored tonight will continue to be asked long after you wake, by physicists in laboratories and dreamers gazing at the night sky, by children wondering why things are the way they are. But for now, the wondering can wait. The muons will continue wobbling whether you watch them or not. The quarks will continue decaying according to laws that might or might not require revision. Let your thoughts drift like virtual particles in the quantum vacuum, appearing and dissolving without urgency, without destination. The universe has existed for nearly 14 billion years and will continue for trillions more. Your rest is well earned. A brief pause in the cosmic conversation. Sleep now, knowing that mystery is not a problem to be solved, but a gift to be savoured. That not knowing is not failure but invitation. That the cracks in our understanding are windows onto wonders we cannot yet imagine. Tomorrow the questions will still be there, patient and enduring, but tonight they can keep themselves company in the dark. Sweet dreams.